The committee will come to order. Without objection, the chair is authorized to declare recesses of the committee at any time. And without objection, I would like to submit for the written record testimony provided by the Quantum Industry Coalition. Seeing no objection, so ordered. I recognize myself for five minutes for an opening statement. Good morning and welcome to the Science, Space, and Technology Committee's first hearing on quantum science and technology this Congress. This hearing could not have come at a more critical time. Quantum technologies, much like artificial intelligence and high-powered computing, are changing our nation's economic, strategic, and scientific landscape. Congress is navigating difficult policy questions on the emerging technologies, and continued American leadership is essential if we want to capture their many benefits. I cannot overstate the importance of maintaining the U.S. competitive advantage in quantum capacities. The global leader in commercial and military quantum applications will have an economic and strategic advantage not seen since the United States ushered in the nuclear age in the 1940s. Quantum sensors developed right here at home already enable many of the functions we take for granted, like keeping time and enabling global navigation and positioning. Further development, miniaturization, and hardening of these quantum systems will give Americans the advantage on the battlefield of tomorrow. Quantum computers have vast, untapped potential for both good and evil, which is why it's so important that we stay ahead of our adversaries on these technologies. On the one hand, quantum computers could help us solve fundamental problems in biology, chemistry, and physics. Quantum computers could model the effects of new drugs at the molecular level, saving time and money in delivering new healthcare treatments. They could help us understand and develop advanced materials that will revolutionize American manufacturing. They can help us develop cleaner energy technologies, ensuring affordable prices with lower emissions. They might even advance the development of artificial intelligence. Imagine the widespread benefits this could have for agriculture. Using the services enabled by quantum technology, we could increase global food security, lower the price of groceries for Americans, and increase production and profits for American farmers. In the wrong hands, though, quantum computers could crack modern encryptions that are the bedrock of global financial systems, communications, and intelligence gathering. We cannot afford to have adversaries like the Chinese Communist Party use quantum technologies against us. Using a quantum computer, the CCP could, in moments, crack current encryption codes, breaking down our digital defenses and exposing businesses and American citizens to gross violations of privacy. Recognizing the importance of staying ahead of the competition, this committee passed the National Quantum Initiative Act in 2018. Thanks to this legislation, the United States has maintained its position as the global leader in quantum research, development, and technology. But our adversaries are catching up. China and Russia are investing heavily in the development of operational quantum systems. China in particular is investing more than $15 billion in quantum research and development. If we want to maintain our leadership role in the quantum field, Congress needs to make smart, strategic investments. But government cannot do this alone. A central tenet of the National Quantum Initiative Act is empowering U.S. researchers and businesses to innovate while the federal government plays a supporting role, where appropriate. The model has worked well, and U.S.-based businesses are leading the pack in quantum applications. As this committee works to reauthorize the National Quantum Initiative for the next 5 years, we must build on this working model while also developing new international partnerships with our allies. That is not to say that there's not an active role for the government to play. The quantum industry, like other emerging technological industries, is in dire need of additional talent to fill out the workforce. The National Science Foundation, the Department of Energy Quantum Centers, established under the National Quantum Initiative Act, have been hard at work to build out our educational curriculum, training programs, and industry partnerships over the last 5 years. These activities could not take place without government support, and I look forward to hearing our witnesses speak about the progress that has been made. The government could also empower the quantum industry through complementary research and technology development. The National Institutes of Standard and Technology is already recognized internationally for its quantum innovations. Congress should enable NIST to further develop its expertise and leadership in solving the many complex science and engineering challenges that enable the quantum ecosystem to succeed. My staff and Ranking Member Loughran's staff are hard at work crafting bipartisan legislation to ensure we maintain our leadership position in quantum science and technology, meet the workforce needs of the quantum industry, and accelerate the commercialization of quantum systems. The dialogue we'll have in this hearing today will inform the development of that legislation, and I look forward to hearing the recommendations of our witnesses on how this committee can improve quantum programs to carry out the National Quantum Initiative into the next 5 years. And with that, I now recognize the ranking member, the gentlewoman from California, for an opening statement.
Well, thank you, Chairman Lucas, for holding today's hearing, and I'd also like to welcome our really quite distinguished panel of witnesses. You know, one of the joys of serving on the Science Committee is that we truly are the committee of the future, and we're doing so in a bipartisan manner. Today's hearing is truly about the technology of tomorrow. As we know, in 2018, the committee led the development in the bipartisan National Quantum Initiative Act and the whole of government research initiative on a topic that seems really ripped out of the science fiction books I used to read as a teen, quantum information science. By all accounts, the first 5 years of this initiative have been a big success. The initiative galvanized the U.S. science community around quantum technologies, and it's made our country a world leader in many quantum applications. I was an original co-sponsor of the Act in the 115th Congress, and I'm looking forward to partnering with the chairman in considering this reauthorization. The first 5 years focused primarily on the fundamental science advances needed to make quantum systems work. While investments in fundamental research need to continue, they are essential over the next 5 years. We're also, as the chairman is mentioning, need to invest in human physical and physical infrastructure that's going to allow us to move quantum technologies from the lab to the marketplace. In my own district in Silicon Valley, companies such as D-Wave and Rigetti Computing are already building hybrid quantum computers that can address novel computing challenges. Now, these two companies are among many companies developing quantum technologies. The nascent U.S. Quantum industry does face significant hurdles to continuing its growth and meeting its potential to hopefully secure U.S. leadership in quantum technologies. One of these challenges, of course, is preparing the quantum-ready workforce. We've not yet had a major focus on quantum education and workforce development, although in the CHIPS and Science Act, Congress updated the National Quantum Initiative Act to promote early introduction to quantum concepts and quantum science among middle school and high school students. Really, it's just a few universities that have created their own interdisciplinary quantum science and engineering degree programs. Significant hurdles remain to getting a ready workforce, and one important topic for this hearing is understanding those hurdles and exploring the role of the federal science agencies in helping to address them. Another challenge, of course, is infrastructure, enabling our universities, national labs, and startup companies to conduct quantum experiments and develop and demonstrate quantum technologies requires state-of-the-art research infrastructure, and this is, of course, a multi-layered challenge. NIST is one of the key federal agencies charged with conducting quantum research, is really in a crisis of failing infrastructure and unmet maintenance needs, and I hope that this committee can address that in our authorizing work. The Department of Energy labs also face challenges. We're asking our federal scientists to conduct exquisitely sensitive experiments in woefully outdated labs. In addition, universities and small companies across the country will need access to specialized equipment that they can't afford on their own. As we look forward into the future, there will be additional challenges that we can start preparing for today and additional challenges that we may not even imagine at this point. I look forward to the discussion today to learn how the reauthorization of the National Quantum Initiative Act can help to address these challenges. And Mr. Chairman, it is a pleasure to work with you, and I yield back.
I want to thank the ranking member for always thoughtful words. And with that, let me introduce our panel of witnesses before they begin their testimony. Our first witness is Dr. Charles Tahan. Dr. Tahan serves as the Director of the National Quantum Coordination Office and Assistant Director of Quantum Information Science at the White House Office of Science and Technology Policy. Dr. Tahan came to Quantum Coordination Office from the National Security Agency's Laboratory for Physical Sciences. He holds a PhD in physics from the University of Wisconsin-Madison. Thank you. Our next witness is Undersecretary Paul Debarr. Mr. Debarr was the fourth Undersecretary for Science at the U.S. Department of Energy, serving from 2017 to 2021. Before entering government, Undersecretary Debarr served as a nuclear submarine officer in the U.S. Navy. He's now the CEO of his own quantum networking company, Debarr Quantum, and he also holds degrees in marine and nuclear engineering and business administration. Thank you. Next, we have Dr. Eleanor Rafel. Dr. Rafel is the Senior Researcher for the Advanced Computing and Data Analytics at NASA's Ames Research Center in Palo Alto, California. She's a published author on the subject of quantum computing and received the NASA Exceptional Engineering Achievement Medal in 2019. The doctor holds 2 degrees in the subjects Americans fear most, math from UCLA and Harvard University. Thank you. And just an observation about the obvious thing in the world out there. Next is Dr. Celia Mertzbacher. Dr. Mertzbacher is the Executive Director of the Quantum Economic Development Consortium, a coalition of quantum stakeholders dedicated to the growth of a commercial quantum-based industry. Dr. Mertzbacher has served in various research and government roles, including stints at the Naval Research Laboratory, OSTP, and Oak Ridge National Laboratory. She earned a degree of science in geology and earth sciences from Brown University and her PhD in geochemistry from Penn State. Last but not least, we have Dr. Emily Edwards. Dr. Edwards is the director of the Illinois Quantum Information Science and Technology Center at the University of Illinois, Urbana-Champaign. Her center is a leader in training scientists across a variety of fields to enter the quantum-ready workforce. Before moving to Illinois, Dr. Edwards was the Director of Communications and Outreach at the Joint Quantum Institute at the University of Maryland. The doctor holds bachelor's degrees in physics and chemistry from Appalachian State University and a PhD in physics from the University of Maryland. Thank you all for being here today, and I want to begin by recognizing Dr. Tahan for 5 minutes to present his testimony.
Chairman Lucas, Ranking Member Lofgren, and esteemed members of the committee, I am honored to appear before you today to discuss the future of the National Quantum Initiative. My name is Charlie Tahan. I'm the Assistant Director for Quantum Information Science and the Director of the National Quantum Coordination Office at the White House Office of Science and Technology Policy, or OSTP. I'm also a practicing quantum physicist with over two decades of experience in academia, industry, and government. My mandate at OSTP includes working with agencies to develop and maintain the National Strategy for Quantum Information Science, a strategy that has been consistently improved over the last few years. It is a privilege to lead the National Quantum Coordination Office, and I want to thank the committee for establishing it under the NQI Act. The value of the NQCO lies in our team of government experts in quantum, detailed to OSTP from NSF, DOE, NIST, DoD, and the intelligence community. Our duties extend to regular interactions with industry, academia, national and federal labs, and the global quantum ecosystem, including our foreign counterparts. Our participation in workforce development and public outreach activities, such as World Quantum Day and the National Q12 Education Partnership, underscore our commitment to building the community. One of the NQCO's most important roles is to facilitate interactions between the agencies. Members from over 20 federal organizations actively participate in the working groups and events that we help organize. The impact of information technology on our society has been profound, and quantum information science represents a foundational shift in our understanding of IT. Quantum information applies the most surprising aspects of quantum mechanics, which are the rules that govern how really small things behave, to how we process, store, and transfer information. Quantum science has already made disruptive impacts via technologies like GPS and MRIs. Next generation quantum sensors will create even more transformative systems for precision navigation and for biomedical applications. Future quantum computers will enable new science as well as chemistry and materials discovery. Quantum networks may one day connect these new types of computers and sensors together. But to get to that future, numerous scientific and engineering challenges must still be overcome. Large-scale quantum computers are also expected to jeopardize existing secure communication protocols. This requires the U.S. to balance the economic and national security implications of quantum. National Security Memorandum 10 on quantum computing, signed by the President last year, addresses these concerns directly. Given this immense potential, U.S. leadership in quantum information science is crucial. The national strategy has three broad goals: getting the science right, enhancing U.S. competitiveness, and empowering our people. The first 5 years of the NQI has succeeded in strengthening the American quantum ecosystem. It has solidified our all-of-nation response, recruited new researchers to the field, and helped spur significant industry investment. Federal funding for quantum has doubled since the NQI's passage. Our success can be seen by those who have emulated the United States, with many countries around the world launching national quantum initiatives of their own. It is critical that the U.S. reaffirms and strengthens its commitment to quantum information science by reauthorizing the National Quantum Initiative Act. By doing so, the U.S. will signal to the world that it will continue to lead in this critical yet emerging field. U.S. involvement is more important now than ever, as it is essential that we continue to work with trusted partners to get the development and protection of this technology right, which includes the rapid deployment of quantum-resistant cryptography. Because of this importance, OS2B coordinated an interagency process recommending policies to the committee to enhance the NQI Act. Here are some of the most important points. First, reauthorize the NSF and DOE centers and remove the limit on the number of designated centers. Second, support long-lived NSF programs focused on training talent in quantum and understanding workforce demand. Third, strengthen the whole-of-government approach by expanding the core agencies. For example, a dedicated international fund is needed to support U.S. commitments in international cooperation. NASA, NIH, and DHS also have important roles to play and can do more. And we welcome further integration of the DoD and the IC. Fourth, we need to begin translating scientific discoveries made in the NQI to commercial utility and agency missions through engineering research and systems integration programs and public-private partnerships. The NSF TIP Directorate, a NIST Center for Quantum Engineering, and the QUEST program at DOE are just a few examples of such opportunities. Finally, upgrade and equip new laboratories across the U.S. so that we can remain competitive with the world. These recommendations complement those of the NQI Advisory Committee, whose first report is now available, and I've included in my written testimony. I will end by reinforcing the importance of people to our success. Training and recruiting talent both here and across the world are the most important actions we can take to strengthen U.S. leadership. Thank you again for this opportunity, and I welcome your thoughts and questions.
Thank you. I now recognize Undersecretary Debarr for 5 minutes to present his testimony.
Chair Lucas, Ranking Member Lofgren, and members of the committee, I'm honored again to be before this committee. My favorite authorizing committee, but please don't tell E&C that. I am honored to be here to discuss quantum technologies and this committee's leadership from 5 years ago on triggering a technology revolution and how this next act can continue that momentum. Not long ago, the prospects of quantum moving from the science lab to applications seemed far-fetched. Barely 6 qubits could be fabricated on a chip, and quantum teleportation was an interesting science experiment at Berkeley. Your act 5 years ago directed significant investments that led to results. It built on the historical efforts of NSF, NIST, and DOE, provided additional supports for universities, a commercial consortium, and the 5 NQI centers, and provided for coordination of national efforts. At DOE, we stood up those research centers with over 70 participants from national labs, academia, and the private sector. This was the first time that DOE Discovery Program included the private sector. Major accomplishments included at Oak Ridge, development of a quantum computing hub, extensive quantum networks tested at Caltech, Brookhaven, Fermilab, and Argonne. IBM fabricated a quantum processing chip with a record 433 qubits on its path to a quantum supercomputer. Google developed a high-fidelity quantum processor and developed quantum simulations, including a wormhole teleportation protocol. And Berkeley lab researchers received the Nobel Prize last year in experimentally proving quantum teleportation for networking. But your accomplishments were far beyond the direct NQI programs. Your efforts were the seed round that triggered a massive set of investments from others. In academia, a wide set of university-started programs, from the University of Chicago's Molecular Engineering School to Caltech's quantum networking efforts, just the Columbia Quantum Initiative, Oklahoma State's Lahiri's Group, and Santa Clara University's Engineering Physics program. You triggered foundations to invest, notably the Pritzker Foundation in Illinois. You triggered a vast set of private investments. Since the NQI was passed, over $6 billion have been invested by the private sector, about 5 times what you appropriated and directly authorized. On Wall Street, that would be called leverage. My quantum networking business, Borg Quantum, and many other companies benefited from this ecosystem. And not only have American companies grown, but quantum companies from overseas have moved to the United States, including in the Bay Area, following your leadership. As you consider the NQI reauthorization, here are a few thoughts on how to build on your successes. We need to bridge the gap between research, quantum products, and users. While still advancing the science, it's imperative to look at first-generation applications and deployment, including private company quantum computers, an enhanced Quest program, and network systems. Stand up a program to design, procure, and deploy at the National Lab's first quantum-centric high-performance computers, and I would recommend deploying a first U.S. quantum satellite program. Here are some specific ideas for your consideration for the second NQI Act. Maintain core research programs at the various centers and adding funding to that. Authorize a new program for first steps of usable quantum computers, networking, and sensing. Would recommend authorizing a quantum-centric high-performance computing program. Authorize DOE to start a $200 million per year post-exascale high-performance computing program that would incorporate quantum into the architecture of the supercomputers. The NQI should build on the momentum of the announcement by IBM, U Chicago, and the 2 DOE national labs to build a 100,000 qubit supercomputer that was announced a few weeks ago, and included our great ally, Japan, in that. We should look at doing a joint DOE-NASA quantum satellite program. We should look at scaling up helium-3 production at Savannah River National Lab, create a new quantum foundry effort in instrumentation, and authorize allowing for allied nations to work together with us. This topic is important to national security. It is no coincidence that when Snowden defected to China, they immediately started ramping up quantum networks and their quantum computing program. This technology is critical around about decryption, as the chairman mentioned, and China, while behind us, is right on our heels. I recommend that we continue to move forward with the momentum that you created for America in this next act.
Thank you. And I recognize Dr. Rafel for 5 minutes.
Chairman Lucas, Ranking Member Lofgren, and distinguished members of the committee, thank you for the opportunity to discuss NASA's role in quantum research and development. I direct the Quantum Artificial Intelligence Laboratory, the Quail Lab, at NASA Ames Research Center in Silicon Valley. Our team focuses on quantum computing and collaborates with other NASA centers on quantum networking and quantum sensing. I joined NASA just over a decade ago to help build its quantum computing effort. Quantum information sciences aims to harness the unique properties of quantum systems to process information in powerful ways. Applications range from computing to networking to measurement, timing, and sensing. Potential NASA applications include astronomical imaging, mapping of planetary electromagnetic and gravitational fields, and aeronautics communication and navigation. When the Quail team at NASA Ames was formed, it followed the model of the NASA Advanced Supercomputing Program. It would not build quantum computing hardware, but rather would form close partnerships with groups that did. NASA's high-end computing capability has long served as early testers for supercomputing hardware and software advances from industry and beyond. Algorithmic work is essential for the ultimate utility of quantum computing. The current prototype Quantum processors are small and non-robust, but progress is rapid, and as hardware advances, we will be able to explore quantum algorithms in ways that are impossible today. NASA, with its many computational challenges, is a rich source of use cases in aeronautics, earth and space sciences, and space exploration. Quantum computing holds the promise of addressing challenges that are beyond what high-performance computing can do. Advances in quantum optics have potential for new networking technologies, both terrestrial and space-based, with potential applications in security, data transfer, and navigation. Quantum networking is key to link quantum computers and quantum information systems. NASA's SCAN program investigates optical networking and has conducted multiple successful technology demonstration missions in the last decade, with more planned. SCAN partners and other U.S. government agencies in areas of advanced adaptive optics for ground stations, space-qualifiable quantum sources, detectors, and memory, as well as to develop quantum use cases. Mission concepts from these joint activities include a space-based quantum testbed. Quantum sensing uses quantum properties of matter and light to achieve unprecedented measurement sensitivity that outperforms classical counterparts. Quantum sensors can impact technologies important for a range of NASA missions, such as timing, remote sensing, metrology, ranging, and imaging. For example, improving gravitational mapping would enable scientists to better understand changes in ice, oceans, and land water on Earth. The gravity recovery and climate experiments have been mapping Earth's gravitational fields. NASA is funding efforts towards a future quantum gravity gradiometer, or QGG, that provides 10 times better resolution. Quantum sensing technologies such as atomic clocks and atomic inertial measurements provide navigation and timing in space and in areas in which GPS is unreliable or unavailable. Quantum sensing technologies can revolutionize NASA's mission to unlock the secrets of the universe, provide insights into dark matter, and connections between quantum mechanics and gravity. NASA's Cold Atom Laboratory has been operating continuously on the International Space Station since 2018 and serves as a pathfinder for future space technologies. NASA and the Quail team have many partnerships with industry, other government organizations, academic institutions, and international entities. NASA has been at the forefront of many technologies. NASA contributed to demonstrating the potential of parallel computing with the first massively parallel computer, the ILIAC-4, coming to NASA Ames in 1972. We are excited to play a similar role in quantum information sciences. Thank you again for allowing me to share my expertise in this area with you and for your continued support of NASA research. I would be pleased to respond to questions from members of the committee.
Thank you very much. I now recognize Dr. Mertzbacher for 5 minutes to present her testimony.
Thank you, Chairman Lucas, Ranking Member Lofgren, and members of the committee. It's a great honor to have the opportunity to participate in today's hearing. I'm Celia Mertzbacher. I'm Executive Director of the Quantum Economic Development Consortium, or QEDC, which is managed by SRI International. QEDC is the consortium of stakeholders that was called for by the NQI Act of 2018. We get, I think of it as startup funding from NIST, and we get some funding from the Air Force Research Lab as well. But increasingly, we are supported by our growing members. We have some 230 members today. About 170 of those are corporate, and about 3/4 of those companies are small or startups. More than 50 government agencies have also participated in QEDC activities, so we're really building a broad, trusted community of quantum ecosystem members. QEDC's mission is to enable and grow the quantum industry and the associated supply chain. It sounds easy, but it's not. We're exploring for use cases of quantum. That's the most frequent question. And in order to realize these use cases and the potential, we're looking for gaps that need to be filled. Gaps in technology, critical technologies like lasers and cryogenics and special electronics. Gaps in standards and benchmarks for measuring progress. gaps in the workforce, and we're providing input on policies like export controls. The NQI was launched with a science-first strategy, which made a lot of sense at the time. We needed multidisciplinary research. We needed teams of researchers from physics and materials and computer science and engineering to come together. We needed to start creating the pipeline of talent. You'll hear more of that from Dr. Edwards. And we did a great job of doing that through the investments under NQI by NSF and DOE in particular. We've had a great start, and those efforts need to be sustained. But other nations are investing as well, as we've heard. Just recently, the UK, Canada, Australia, Japan, India, Germany, I could go on, have all released or renewed their national strategies. And they're all funding the science, but they're also focusing more on the application and commercialization. China is investing a lot. Some reports say $15 billion. They're hard numbers to verify, but the number of high-quality, highly cited research publications and patent applications indicate that China's research and industry in quantum is growing as well. The private sector is making big bets too. I think most of you, if not everyone, has heard about some of the large tech companies' activities. They're developing products with their own resources and making big investments. There's a growing number of smaller, pure-play quantum companies. And I'll remind you, there are no big quantum companies today. These small companies have private investment. Some of them are getting some government funding as well. But the venture funding seems to be slowing, according to a McKinsey report last year. And so it's really important at this time for government to take measures to de-risk the technology and to bridge to the quantum economy of the future. We're here, and I noted the title of this hearing was Ensuring American Leadership in Quantum Technology. Technology is the application of science. And so I'll leave you with some suggestions for how NQI could be improved in light of the economic potential and the accelerating global competition. First of all, expand R&D to address gaps on the pathway to the quantum economy. For example, we could try some new programs that really fund industry and academia to work together, focusing on small businesses. This could be done in the NSF TIP Directorate. TIP stands for Technology, Innovation, and Partnership. Sounds like a good fit. Fund Quest. Thank you to this committee for authorizing Quest. It's becoming urgent to fund the program, which is to provide access to researchers broadly from industry, academia, government labs to quantum computing resources. Other countries are standing up similar programs. We need to fund this one. Provide for upskilling and reskilling of the existing workforce. We need to build the pipeline, and we're doing a great job of starting that, but we need people today. And so we need to fund the workers. And I want to just mention in my closing to take full advantage of NIST. NIST has gotten 4 Nobel Prizes in quantum technology. They do standards, metrology, advanced manufacturing. They run the CHIPS R&D program. So NIST should be a bigger part of it. And I'll finally end by cautioning about being careful when it comes to using export controls to control this technology. It's early. Any controls should be done multilaterally, or we won't achieve our goals and risk hampering U.S. business. Thank you, and I look forward to your questions.
Thank you. And I now recognize Dr. Edwards for 5 minutes to present her testimony.
Thank you, Chairman Lucas, Ranking Member Lofgren, and distinguished committee members for the opportunity to testify today before this panel. I'm Dr. Edwards, and I co-lead the National Q12 Education Partnership through a grant from the National Science Foundation. This consortium was spearheaded by the White House Office of Science and Technology Policy and NSF. I also co-lead education and workforce programs for one of the NSF Quantum Leap Challenge Institutes, Hybrid Quantum Architectures and Networks, and that's at the University of Illinois, University of Wisconsin, and University of Chicago. We've heard a lot about the importance of quantum to our nation. And we've heard a lot about things we must do and, in order to strengthen our leadership, including reauthorizing the NQI and continuing federal advancements. It's really amazing what we can do today with quantum. And I'm just so excited to talk about it because it's one of my favorite subjects. For success in the long term, we need to invest in programs that significantly expand the participation of teachers and educational institutions across the country. And I really appreciated the opening remarks by the chairman and by Ranking Member Lofgren. This approach recognizes that scaling the quantum workforce relies on empowering educators as mentors, role models, and ambassadors. Moreover, the public of all ages should have a front row seat to the development of quantum information science in places like museums and libraries, so that they can be prepared for a future that is influenced and underpinned by emerging quantum research and technology. The Q12 has been convening stakeholders around the development of a quantum workforce that draws on diverse strengths and backgrounds of people across the country. And we've had a lot of meetings. And we see that there is wide agreement that students need exposure to quantum information science early to ensure continued U.S. leadership in this fast-evolving field. This is reflected in the CHIPS and Science Act, which calls on NSF to increase the integration of quantum into STEM curricula at all levels, establishes a quantum education pilot program, and requires a workforce assessment study. And I want to thank Congress, and in particular this committee, for including these provisions in the legislation last year. Currently, there are a lot of early stage programs, and many are connected to Q12, that are increasing quantum readiness by expanding access to the field. And the National Quantum Initiative Act reauthorization is an opportunity to double down on this. Currently, we are missing resources for K-12 teachers. At higher levels, and Dr. Tahan mentioned this, educators broadly need cutting-edge labs to teach the next generation and provide upskilling for the current workforce. Essentially, we need more education and training opportunities for students, which are two different facets of workforce development, and they need to be readily available no matter where you live in this country and no matter your background. And this is important for addressing the persistent lack of diversity across quantum-related fields, as this contributes to severe shortages and limits our competitiveness as a nation. There are a lot of programs that are working to remove barriers to this field, but it's going to take time. You heard about the mention of World Quantum Day. These and other educational programs under the National Quantum Initiative Act are helping to dispel the notion that quantum concepts are only accessible to the very few. Rather, quantum can provide inspiration for young learners and teachers alike and empower them to understand a host of emerging technologies that are so vital to our nation. In this context, I'll highlight two elements that are possible opportunities as you look to reauthorize this act. First, I urge the committee to consider authorizing at least one national center for quantum education and workforce that will accelerate the readiness of educators and serve as a resource for existing programs to scale their local impact in communities across the country. A center-scale investment will concretely link the different parts of the educational pipeline and the different sectors and include the public. A new center could amplify and connect the initial workforce programs that have been developed, such as those supported across the many agencies. And it could provide an avenue for the much-needed comprehensive regular workforce studies. Second, there's a critical need for investments and public-private partnerships to build modern facilities, and we heard a little bit about this. Expanding quantum educational programs will help American workers have depth and agility over their careers and allow more people to prepare what comes next, quantum adjacent, or whatever else is down the road. And I want to just take a moment. I know I'm at my moment at time, but I want to take a moment and say that, I was reflecting yesterday on the National Quantum Initiative Act, and I look back 20 years, which predates it, and it's around this time of year that I spent a summer at NIST as a second-year grad student doing quantum physics research. It was my second time at NIST because I also spent a summer there as an undergrad coming from a small college. These experiences and the teachers who guided me have been integral to my path into quantum and my career today. And I hope this reauthorization expands such pathways for more students and more educators across our country. Thank you for your time, and I'm happy to take questions.
Absolutely, and I want to thank the witnesses for your truly outstanding testimony. The chair recognizes himself for 5 minutes. Dr. Tahan, the National Quantum Initiative focused on advancing fundamental quantum research across several agencies. Fundamental research is generally open and available for public consumption, even in areas with advanced technological potential. Unfortunately, we know how China is happy to let the U.S. advance fundamental research while it overinvests in the development of leading-edge applications after the fact. In the next 5 years of the National Quantum Initiative, how can we safeguard our research investments while maintaining our core scientific values? That's a big question, but it is important.
Thank you, Chairman, for the question. It is important. It's a question that goes beyond quantum, the question of research security in a new world. I will say that this is something we take very seriously in the White House, in the subcommittees that oversee quantum in OSTP. One of the first things I did when I became director was launch a fast-track action committee on the role of international talent and research security in quantum information science. That report is available. We can make it available to your staff and follow up on it. Some of the recommendations that were made in that policy document, and these came from all the agencies, include having the agencies write technology protection plans. Even fundamental R&D agencies like NSF, those ultimately became directives in National Security Memorandum 10. It is something we follow on every year to help coordinate and share best practices across the agencies, from the DoD to the IC to the FBI to the NSF and DOE. We have a subcommittee, the Economic and Security Implications of Quantum Science subcommittee, that's completely dedicated to that, sharing best practices among the people who are actually running the programs. There's no perfect way to manage risk, and first and foremost, our goal has to be to continue to move fast, empower our scientists and entrepreneurs, keep the open scientific community. This is a unanimous view from the agencies. We need to keep our open scientific engine of discovery going, but we need to do it in a smart way in this new world. And that comes down to really knowing what's going on across the world and in our country, what the risks are, and making good decisions.
Dr. Edwards, each of our witnesses touched on the need for more quantum workforce development investments. You run an education workforce center now, and you recommend Congress authorize the creation of a national center for quantum education workforce in your testimony. What would be your vision for such a center, and how do you see it meeting the needs of a diverse group of quantum stakeholders? Give you another big picture question, too.
Let's see. I was trying to figure out which indicated talk. No, that's a really, really great question. So for clarification, so the Q12 partnership is a consortium, a voluntary consortium. And so currently we're setting up scaffolding. And over the last couple of years, it's become clear that what is needed is to build on this scaffolding to have a national center that can provide a resource. The role of such a center, in this case, is to draw together the existing workforce efforts and leverage them. So basically, the centers are doing awesome at the science, and they're really articulating the need for a workforce, but their original scope was not at the K-12 and undergraduate levels. And given that their original scope was not there is not necessarily resources to scale the impact of the nascent programs they are doing. And so I think a national center serves as a resource to scale and to also build into communities that are not being reached by the current National Quantum Initiative investments.
Teeing off of that, using the phrase national center, should Congress create more than just one workforce center under a single agency, or should we promote multiple centers? So
this is a great question. So I think, another great question. So I think there are two approaches. What we need to do is the goal when we design a center or design a resource is to remove barriers. And so I would say it would be ideal to have a center that is co-funded by multiple agencies, because this will serve to remove the barriers that exist between the different investments across multiple agencies. We really want participation and to leverage efforts that are at the whole of government. In the absence of that, if it makes sense policy-wise, then I would say you would need multiple centers if you're not able to have one that kind of pulls in the whole of government.
My time has expired. I now recognize the ranking member, Mrs. Lofgren, for 5 minutes.
Thank you, Mr. Chairman, and thanks to the witnesses for your really fascinating and wonderful testimony. One of the questions and most of you have mentioned NASA, and it's great to see someone from NASA Ames. Thank you so much for traveling here to be with us. Is there anybody who doesn't think that NASA should be added as a member of NQI? Should we add it? Everybody's saying okay. So I think that's something I'd like to explore with the majority. I'd like to follow up, Dr. Mertzbacher, with the testimony you had about the gap between science and application, and how, kind of the valley of death if you're in Silicon Valley. Could you be more detailed about what we might do to enhance the delivery from the lab to the commercial market? What are some of the things that we could do to enhance that effort?
Yeah, this is not a quantum-specific problem, of
Correct.
course. But I view quantum as sort of a poster child or a pilot project. We can focus on this. It's the emerging technology today, and we can get it right. And so some of the approaches that could be taken to move some of the research that's got practical application into the marketplace is to better connect the industry and academic researchers. And I run into this problem of capacity at some of the small companies to even do longer-term research. So we've got to somehow better connect the two, and that's where perhaps some programs at places like NSF TIP could help. We also know that there's going to be manufacturing and scaling up challenges. Right now, even at the companies, if you go and visit them, it looks like a research lab. It's a big, complicated system that takes a lot of people to keep it running. And we need to be integrating these things and scaling them up and making them more reliable. And so there's manufacturing challenges and manufacturability challenges, and programs like the Advanced Manufacturing program that NIST runs, and that's supported by other agencies as well, is an opportunity. We could create an Advanced Manufacturing Institute. I'll remind you all that under the CHIPS and Science Act, DOD is creating some hubs for prototyping, and they have said they want to make one of those focused on quantum. We're very excited to see what the outcome of that competition is. So we'll have some prototyping capability. If we can get some manufacturing capability to go along with the research piece, I think we have the whole sort of innovation chain.
How much do we allow the private sector in to utilize facilities that are funded by the federal government?
Often they're welcome. I'm on the board or advisory committees for some of those user facilities. When you look at the numbers, there are not as many from industry, and that's often because maybe they don't know about it. There may be IP issues that always comes up, but I don't think that's necessarily standing in the way. I think it's getting more, making it easier. And sometimes there's really just a capacity problem. And so when I look around and say, where is the capacity for doing some of that early stage work, it's in the government labs and universities. So we need to connect the people in both sectors.
Dr. Edwards, let me ask you about the workforce issue. Obviously, when I first was considering this, I thought, well, why would we do K-12? Because, a senior in high school is not going to be prepared to go into quantum physics. But the more I thought about it, the more I thought, actually that is helpful, because quantum seems at odds with the world as we see it. And, when I first read Schrodinger's cat, I'm going, this is so weird. And so it would be helpful for young people to actually wrap their heads around that so that they could move on at a later date. We can't be in every classroom, and not every teacher wants to do this, but have we thought about creating a model curricula that would be available to schools or teachers who wanted to do this, that they could just download it and print it as a way to getting this across the nation?
Yeah, thank you for that question. Yes, so through the Q12 and the grant CUTA work, we've been able to develop an initial framework that's a precursor to curriculum to infuse quantum into the STEM subjects at the high school level and also at the middle school level. And this is an approach led by teachers, and I think that it's a way that recognizes the diversity of education approaches across the country. The next step is indeed to develop a model curriculum, and this is part of why we need a center, because such a center would develop the appropriate curriculum so that teachers and school districts, and then even primarily undergraduate institutions, could flexibly adapt it to the needs of their classroom. Because after all, the teachers, the educators, the communities, and the families, they know how to best communicate these complexities to their young people.
Thank you. I see my time has expired. I yield back, Mr. Chairman.
Thank you. The chair recognizes the gentleman from Florida for 5 minutes. Mr. Posey.
Thank you very much, Mr. Chairman. I thank the staff for putting together such a great and informative panel. It's really been an interesting hearing. What additional safeguards does the National Quantum Initiative need to put in place to prevent countries of concern like China from stealing our research? Dr. Tahan touched on it, and I'd kind of like to get the opinions of the other witnesses. Left to right, it'd be fine.
Congressman, so one of the things that we did at DOE around all technologies, but quantum was a part of it, was develop something called a technology risk matrix, which was actually to list technology by technology of what's okay to work with on an open science basis, and what is, although it may not be classified yet, that it should be restricted on engagement with countries that are adversaries. I'd recommend that while DOE has that, I would recommend that other agencies also look at that screening process also.
Thank you.
I'm a technical person.
turned it off.
Oh, I turned it off. Oh, okay. I'm a technical person, so I just want to say that I'm aware of NASA's strong export controls, and we vet foreign nationals coming into NASA. We look at documents going out of NASA, et cetera. And for a stronger answer, I'll defer to other experts at NASA and at other agencies.
So I'm here representing the industry side, of course, and I come up with a term I call business security. And my members need to understand that they are making decisions every day that take them along a path that leads to a position in the future that may or may not be business secure. They're accepting investors. They need to understand who those people are. They need to be making really smart decisions. And to help equip the members of QEDC, I have a very good relationship, actually, with the U.S. law enforcement agencies, and they come in and talk to these companies, especially the small ones. They don't have someone whose full-time job is doing export control, right? So they need to have access to resources, and we're really fortunate to have that relationship that we can use to help them get access to useful information that they can use now to be business secure in the future.
Have you noticed any attempts to capture any of our resources and knowledge?
I assume it's happening. I feel like a Q is a big target. I know that there are occasions when companies have talked to some of our friends in government. I'm not in the middle of that, so I'm not aware of all of it, but I think the relationship has been very useful. And the government people remind us, once the secrets are out, it's too late. We need to be catching those problems before they lead to breaches and leaks.
Thank you. Doctor?
Thanks. So I think mine's maybe just a little bit different to complement what's already been said. I think, at a university, so I'll wear my IQuest hat for a minute as executive director of a quantum center there at Illinois. Academia has in place export controls to follow the laws that are out there. But I think an open dialogue on how these are implemented and how these, what is export controlled and what is not, that is continuous, because the technology is advancing so fast and the research in the labs at the universities changes really fast. And we also have a significant graduate programs that serve both domestic and international students. And that is creating a very lively and robust enterprise in the US. And so we want to keep that in place. So I think the key at the university level is to ensure that there's open communications as these export controls are developed, that recognize the role of academia and the role of industry and the role of government, how we can work together to make sure that as they come out of the labs, they are safeguarded.
Thank you. Dr. Tahan, any further thoughts? I mean, you can go to any trade show in any industry in this country and look at the new products that come online, and a week later, they're duplicated from China. Almost any industry in this country.
I'll make two quick comments to add to my previous ones. One, I think it comes down to making good decisions at the beginning, like Paul said, that if it's fundamental research, let it be fundamental research. If it's technology development, how are we going to protect it over the long run? The second thing is, for emerging technologies like quantum, we need to get in early. So bringing the FBI in, our recommendations for bringing DHS in to help the companies secure their cyber networks. We need to be proactive in doing that early. Waiting till CFIUS and other things, that's way too late. Yeah. We need to be very proactive with emerging technologies and get people educated, help them with their cybersecurity, and then eventually have guidelines for physical security and so on. But it's really an early game here, and that's what we've been working on.
Thank you. Thank you all. Mr. Chairman, thank you.
Gentleman's time has expired. The chair now recognizes the gentlelady from Michigan, Ms. Stevens, for 5 minutes.
Well, thank you to everyone who has showed up for quantum today. This is really remarkable to see the Science Committee packed on such a critical and global shaping topic that we are eager to see the United States lead on. Recently, I represent southeastern Michigan, a county called Oakland County, and we have Oakland University in my district. And recently, Oakland University and their band of researchers alongside Argonne National Laboratory discovered a breakthrough to help lay the foundation for future advancements in quantum computing. These scientists uncovered opportunities for manipulating quantum information by coupling magnetic behavior to a superconducting circuit, thus potentially creating a sort of quantum disk drive with mind-boggling amounts of storage. We're really excited about this. And this research, as many of you have articulated in this phenomenal panel of witnesses, is happening in universities and think tanks all over the world. And one of the major barriers to research, development, and education in quantum information science is the relative lack of shared research infrastructure and instrumentation. The National Quantum Initiative Advisory Committee released a report just last Friday, and we're glad to have these guys on speed dial calling for Congress to invest in infrastructure for quantum in the reauthorization of the Quantum Act. So, Dr. Tahan, can you talk about the scientific community's needs for quantum-related research infrastructure and what Congress should be doing to address these challenges in the reauthorization of the National Quantum Initiative Act?
Absolutely, I'd love to. I think that the important thing to keep in mind here is that if we want to lead the world, we need the people to do it. And so we can't rely anymore on the top 25 universities generating talent. We need to expand the capacity of the United States to generate talent wherever it is. And really, to make that happen, we need to do a few things. We need to educate.
Expand talent and keep it here.
And
right?
keep it
Yeah.
here, right? And wherever they may be, So at the end of the day, that's what I'm passionate about. We're all passionate about. That's what we need to do. To do that, we need to educate people that this is a great opportunity. That there are great careers here for our young people. We need to incorporate much more universities, community colleges, other places of learning and training into the leading universities, the R1 schools, and that means investing in infrastructure, equipment, even small labs, so people can be trained up. We need to get, quantum computing test beds that students can learn in 1,000 schools, not 20 schools.
And you see a return on such an investment, right?
I think there's a great, and I like, this is what I always say, quantum is more than quantum physics. If you think about what it takes to build a quantum computer, or a quantum sensor, or a quantum network, what are the skills you need? How to design a circuit, how to do microwave and RF engineering, how to do programming. Like, those skills in any industry of the future are going to be valuable.
Well, and
whether
Dr.
quantum pays that or
Rafel's
not.
career sort of represents that in many respects, artificial intelligence to quantum, now at NASA. And so, we'll find the bookend to spend a couple of days with you and your career trajectory. But I just want to get in for the record here, because we have these manufacturing institutes, Manufacturing USA, and there is one in Rochester, New York, not in Michigan's 11th district, but in Rochester, New York, called AIM Photonics. And I'm just curious, and I see Dr. Mertzbacher nodding and Dr. Edwards, are any of you working with AIM? Can you tell us about that consortia experience, particularly on talent, R&D, and some of these broader challenges that we're talking about here?
Thank you. Yes. So we actually put in from a team that we put together from within QEDC and others, a proposal to this DoD prototyping call for proposals. And AIM is one of the partners because they have capabilities. The idea of being able to make things, and as I think Charlie Tahan said, or someone else, quantum is really about light and matter interacting, and AIM Photonics is about managing light, making these compact systems, and these photonic integrated circuits that they make are critical to future quantum systems. So AIM is a great part of the ecosystem. That
I'm wondering if they're going to rebrand and start calling themselves the Quantum Lab. But certainly the photonics component of it is deeply important. And we'll ask for the record, because Dr. Edwards, we want to continue to get you in here as well, about the need for the technology dominance for the United States, the strategic investment, what my colleague on the other side of the aisle was talking about with regard to export controls, and how some of your enterprises, in addition to a federal public-private partnership that we have with Manufacturing USA, is helping us to achieve that goal. Thank you, Mr. Chair, and I yield back.
Time has expired. Chair now recognizes the gentleman from Texas, Mr. Babin, for 5 minutes.
Sir, thank you, Mr. Chairman, and Ranking Member Lofgren. We really appreciate all of you witnesses being here. It is a fascinating hearing, and we thank you. Dr. Debarr, I'm glad that you mentioned in your testimony the impact that quantum has on our national security, specifically when it comes to certain defense capabilities that we have or want. Can you please elaborate on our network systems and how we can strengthen these systems to prevent vulnerabilities and damage from our adversaries? And then also, can you share where China is in this same technology?
Yes, Congressman. So I'll start with China. So China is, especially in the networking topic, as you asked about, has accelerated their efforts in some respects farther than us. As I mentioned, after Snowden left and defected, he laid out how efficacious NSA is. And amazingly, they massively built out a quantum network from Shanghai to Beijing, which is not close. They are not close to each other. They also launched a quantum satellite 6 years ago, okay? And so when I mentioned about how networking and satellites and security and codes, they started doing that 6 years ago. And as I look at NASA and others, people have been pitching internally at NASA and elsewhere for us to go do that, and that hasn't happened yet. And so I think leadership from this committee for us to catch up on some of those areas. On the positive side, when it comes to entanglement and the high end of distribution of quantum data and networks, the U.S. is by far the leader in. And so the ability for us to take the CHIPS Act and some of the infrastructure build-out authorized in that, and for whatever you feel is appropriate to authorize in the NQI to accelerate that further. The U.S. is ready to deploy the highest-end quantum networks that will be helpful for quantum computing networking, as well as security.
Absolutely. Can you please share why we're behind China in the quantum satellite efforts? And you alluded to that right then, but and what can we do going forward? You mentioned leadership, especially from this committee, because I don't believe that we can afford to continue to delay making moves to catch up, especially in encryption and some of these fields with quantum. If you can elaborate a little further.
Yes, Congressman. So I think America's ready at your direction and your authorization between the photonics works at NIST, at DOE, and at NASA to actually design a quantum satellite, probably in conjunction with some of the NASA labs and DOE labs, and provide miniaturization of the photonics, get it on chip, and be able to get it down into a package that can go up in a satellite. I think the interaction of that with the terrestrial networks that should be bid out under the CHIPS Act. So the likelihood of New York winning a terrestrial network, a land-based local network, Chicago also winning one, probably one in California, probably one in Oak Ridge and East Tennessee, all likely winners, and taking downlink stations with the satellite and start networking across the country is within the technological capabilities with your leadership.
Outstanding. And what are some ways that DOE can better collaborate with the industry on existing and future initiatives, and how are agencies already engaging with the private sector to meet the needs of our national security space? To you, Dr. Debarr. And if I have time, then someone else can answer as well.
So one of the strengths of your last act was that it authorized efforts between government and private industry. That was kind of leading edge for an early discovery science. First time it was, I think, really ever done. So it can continue to be enhanced, but your last act was really groundbreaking on that for something so early stage and collaborative. I think that as you look at authorizing a big quantum computing program, building on what was just announced in Illinois and with New York, with a lot of private sector leadership, to be direct, I think if you authorize programs for government to continue to be potentially the first owner of those systems or customer of those systems, just like when Dr. Mertzbacher's organization in 1969 controlled the internet, with the first nodes was controlled by her organization, and that was a great example of DARPA and Stanford at the time.
Gentlemen,
Thank you, and I'm out of time.
Gentleman's time has expired. The chair now recognizes the gentlelady from North Carolina, Ms. Ross, for 5 minutes.
Thank you for holding this hearing, Mr. Chairman, and to Ranking Member Lofgren, and thank you to all the panelists for being here today. I'm proud to represent North Carolina's 2nd Congressional District in the Research Triangle and home to the IBM Quantum Hub at NC State University. Since its opening, the IBM Quantum Hub has been a center of quantum computing, education, research, development, and implementation. I also recently visited the Duke Quantum Center, a unique vertical quantum institute located just outside my district, which I believe Representative Fouché will be telling you all about. It's a really, really cool, you actually get to see the computers, the inside of them. It's really cool. Anyway, I'm excited about quantum advancements being made in our home state of North Carolina and look forward to your testimony. I do want to point out one of the major barriers to research, development, and education in quantum information science is the relative lack of shared research infrastructure and instrumentation, and I heard a lot about this at Duke. The National Quantum Initiative Advisory Committee released a report just last Friday calling for Congress to invest in more infrastructure for quantum in the reauthorization of the Quantum Act. Dr. Tahan, could you talk more about the scientific community's need for quantum-related research infrastructure and what Congress should be doing to address these challenges in the reauthorization of the National Quantum Initiative Act?
Yeah, thank you, Congresswoman. We worked very hard, the advisory committee, to get recommendations to inform you all as you were writing the new legislation. One of those, as mentioned, and also in the agency recommendations, was a fund for infrastructure investments across the country. This could take many different forms, but in terms of the science, it's how do we give researchers access to the tools that can sometimes cost $3–5 million a piece in a more efficient way such that we can move the science forward. You know, you don't want to become a professor at NC State and then have to wait 5 years to get the tools in place to actually do your job. And this is something we hear about from many different professors across the country. So one way to do that is to create programs like the Qubit Foundry program to make devices and give them out across the country, have centralized places like Lincoln Labs, national labs that make the qubits, or from industry, make the qubits and give them so that the science can be done on campus with students, and we can come up with new ideas. Another way is to provide sources to equip labs those things are not typically done within the R&D funding program at the agencies. It really has to be an addition that's purely for equipment and an investment around that. So that's really what I think the greatest opportunity is.
Okay. And Dr. Rafel, how does NASA currently fund and share research infrastructure?
We have broad collaborations with industry, with other government labs. We're also part of 2 of the National Quantum Initiative centers and have access to the technology there. One of the really exciting things, to build on the previous question, has been to see hardware moving from place to place as opposed to staying in one lab. And as we work with other agencies and across the different centers at NASA, we expect to be able to support these efforts in really phenomenal ways.
Thank you very much.
Sorry, can I
Sure.
jump in?
Absolutely.
Just,
And my next question was for you, so you can take the remainder of the time.
Oh, well, if you would like to ask it.
No, go ahead.
Okay, I just wanted to underscore this need for infrastructure through an educational lens. So at Illinois, and I believe the vision also actually at Duke Quantum Center, of which I've also visited, Dr. Monroe was my postdoctoral advisor. But at both Illinois and there and other places, we're talking about user facilities and open access educational test beds to cross-train students and even be flexible to do upskilling of the current workforce. I think there's a risk right now that with the current investments, people don't have access to easily get into these, particularly students. And so I see a need that you could build educational test beds coupled with user facilities at universities to provide access to electrical engineers, computer scientists, physicists, because we still do need them, even though it's not just physics, mathematicians and others to work at the different levels of the pipeline from K-12 all the way to upskilling.
Thank you, and I yield back.
Gentlelady yields back. The chair now recognizes the gentleman from California, Mr. Garcia, for 5 minutes.
Thank you, Mr. Chairman, and thank you to the witnesses. A very important discussion here, obviously. I think we're at a really meaningful part of our nation's history. I actually view this technology, quantum coupled with AI and machine learning, as the 4th offset, the 4th military offset. The first offset, if you recall, was our nuclear programs, the Manhattan Project, the propulsion programs that paralleled that. The second offset being stealth technology and the technologies that were derived from that gave us this asymmetric advantage over our adversaries on the global stage. I think the third offset can best be defined as the autonomy and miniaturization of systems that yielded things like the B-2, the B-21 now being produced in my district, as well as UAVs en masse. And I think that the fourth offset, like I said, is now the ability to overlay the quantum computing and underpin the AI and machine learning by quantum to fully enable the processing of data, the data management systems, the networks of networks, the information flow on the fronts, the military fronts specifically. When you look at it through that paradigm, it puts a little bit of a different importance on these programs, and I think given sort of the nascent position of some of these programs, and first of all, I think we're also drinking our own bathwater a little bit relative to China's progress. I think we are trying to have a self-fulfilling prophecy that China is not doing the same investments and not making the same progress that we are. I think they actually are keeping pace and they are spending as much money. It may not be visible to us, but they're utilizing an entire commercial base in conjunction with their military operations. So I think we should be paranoid about their progress and not assume that we have a technological advantage or even a funding advantage in many cases. I think it's very important to look at it from a disadvantage perspective in a paradigm that we need to catch up so that we keep our foot on the pedal and we gain efficiencies. But I also think, because it is the fourth offset, and I really believe that from a security perspective, to your point, Dr. Tahan, we need to be proactive. And I don't get the sense across the disparate agencies, the government side and the commercial side, that we are actually putting in place the security protocols, and not on the fundamental research, but on the actual technology development, the higher end technology development that could feed into weapon systems. My concern is that we are not vetting all of the folks that are working these programs to the levels that we should. Do we have insight into how many Chinese nationals are working these programs? Have we done background checks? These don't necessarily need to be classified programs, but do we manage and keep track of the personnel working these technologies that are feeding into our fourth offset? My concern with the CHIPS Act, I ended up supporting it, but I spent probably 6 hours in the SCIF talking to Intel and Department of Commerce and Department of Defense, that the investments we were making in chips didn't port cleanly to DoD applications, that we were focusing on 7, 9 nanometer wafers and not looking at the smaller wafer chipsets that would go into hypersonics. The second concern I had is that we weren't porting over the requirements for supporting quantum development. I don't recall seeing any sort of specific tailoring of the semiconductor development to quantum computing, whether it's quantum dot arrays or the layers and substrates needed to do what is necessary for quantum computing. And the third concern I had with the CHIPS Act was that we weren't looking at how to protect the intellectual property across all of these efforts. They're all evolving on separate islands almost, and we're allowing for venues to share information, which is good. We've got to be able to share information, but we also have to protect that information from the CCP, and then also make sure that the folks working these programs are vetted and not effectively getting educated here, getting smart on the technology, and then going back to mainland China, where they may not have a choice to share the information. So I've used up my time just talking about this, but I'm really concerned that we as a government right now are not looking at this as a national security program, and that we are only looking at this as sort of a commercial program, maybe not only, but not enough emphasis on the national security implications of this. The idea, the OPM data breach from several years ago, the only thing really keeping the Chinese from really leveraging that data against us is their ability to compute and manage that data. So I'll end with that. I don't have any questions. Ms. Edwards, the Quest program, I'd like to take it offline. We're going into markups for appropriations, so if you can help us understand that need, I yield back, Mr. Chair.
Gentleman's time has expired. The chair now recognizes the gentleman from New York, Mr. Bowman, for 5 minutes.
Thank you, Mr. Chairman, and thank you to all the witnesses for being here. The CHIPS and Science Act is intended to promote domestic development, manufacturing, and testing of advanced semiconductors, and the definition in the bill is specific about semiconductors. However, companies like SEEK, based in my district, are designing and manufacturing more advanced chips for scaling quantum technologies using superconductors. Superconductors are useful for quantum computing, quantum and classical sensing, and other cases outlined in the NQI. Does anyone have thoughts on the role that superconductors could play in the advancement of the quantum computing industry? and what might be needed from Congress or the administration here. Mr. Debarr, I will turn it to you first, given the Superconducting Quantum Materials and Systems Center managed by the DOE.
Yes, Congressman. So Westchester County is certainly a leader in quantum technologies. SEEK in Elmsford has some very interesting control systems which could lead to scaling of quantum chips well beyond what most people are talking about. IBM has obviously made significant announcements in Westchester County and their operations. And then finally, the Chips and Science Act authorizing a quantum network to be bid. I think it is extremely likely that New York will win, and there'll be networks not only in the city and Long Island, but up to Yorktown and Westchester. The support for those sort of efforts, I think, would be critical. And I think one of the things that people don't see is that companies like IBM, like SEEK, like what's going on in Brookhaven, are far beyond basic science. And I think first deployments in conjunction with the private sector, as you mentioned, but also with universities and labs, including in New York, are ready. And so that's why when a number of people here talk about first deployment and cooperative between universities and labs and companies, it's ready.
Awesome. Would anyone else like to just add?
Oh, it looks like a lot of people, but maybe I will just very quickly say that the one thing that in my experience with the superconducting technology is that the ability to make high coherence qubits is a grand challenge that Dr. Tahan is familiar with deeply. And I think that it relies on currently infrastructure from a few companies that are overseas in order to successfully make qubits. We have a piece of equipment at the University of Illinois that we waited 12 months for, and it's one of the only pieces of equipment in the world that's known to make successful high coherence qubits using superconductors. And so at least that it's publicly available. And it's very expensive. So when you ask what people can do, I think it's important to look at these investments to build up the supply chain. And of course, I think the panelists have other comments.
We're really excited as part of the NASA Quail team to be part of C2QA run out of Brookhaven and SQMS run out of Fermilab, which both do superconducting technologies and have really advanced that. Thank you all for supporting those centers. I want to mention that in addition to doing faster computing, superconducting technologies and other quantum technologies have the potential of reducing energy consumption for the computation, and that's another real advantage that we can push on here. So thank you again for your support.
And I'll just add that SEEK is actually a member of our team that put in this proposal to develop prototyping capability. They're a key facility that we hope will be able to grow so that the broad community can use their expertise and capabilities to make these systems.
Please.
I've been working on quantum computing for most of my career. We make some chips at SEEK in my home lab. It's a great lab. I'll just say, in terms of what Congress can do, as the Chips and Science Act is implemented, there is about $11 billion in R&D in the National Semiconductor Technology Center, advanced packaging. If we can ensure that emerging technologies or quantum are covered in the implementation of those R&D facilities, that's the greatest opportunity, frankly, probably of a generation to ensure that we have continued technical leadership of the next generation of IT. So facilities like the DoD Commons, that's something that we worked on internally to encourage quantum to be part of that, but also as the NSTC gets stood up, that they include exotic materials like superconductors, optics, other things that will matter beyond CMOS to future quantum and other types of technologies like neuromorphic computing.
Thank you, Mr. Chairman. I yield back.
Yields back. The chair now recognizes the gentleman from California, Mr. Obernolte, for 5 minutes.
Thank you, Mr. Chairman. Thank you to our witnesses. It's been a fascinating hearing on a really important topic. I think we're all in furious agreement on a few things. First of all, that NQI should be reauthorized. Second of all, that we need more people and more money. We have talked about a couple of problems, and I think every single witness has brought up these problems in your testimony. One, the problem of enabling a quantum-skilled workforce and growing that workforce. And then the second problem of commercializing some of the technology that's been developed in labs and in academia. And I think everyone at the table mentioned this problem. I want to point out that these two problems are related, because if we can solve the second problem solves the first problem. If we get more commercial application, you're going to get more private investment, you're going to get companies that are delivering these solutions to market. They are going to create jobs, they're going to create pipelines into their companies, they're going to create their own training programs, and that'll make this self-reinforcing cycle that solves the first problem of the quantum-educated workforce. Ranking Member Lofgren asked a great question on this about how we start doing that, getting these applications out of the lab and into commercialization. And the answer was generally, we need better communication between the labs and academia and commercial companies. I'm not sure I agree. Count me skeptical on that, and here's why. I mean, I think the problem that we're facing is that most of the potential applications for quantum computing technology are largely still theoretical. It's great that IBM has a chip with 433 qubits on it. You know, that's amazing, way more than we thought we would have at this point. But we're still going to need millions, if not tens of millions of qubits to solve the kind of computing problems that traditional computers are unable to solve. And we still have, as has been brought up, we still have some technical problems to solve, like the problem of decoherence before we get there. So, you know, I really think we need to identify the low-hanging fruit, some applications of quantum computing technology that we can start to commercialize now while we're working on these longer-term solutions. So, Mr. Debarr, you're the private sector guy here. Do you agree with that assessment? And what are the low-hanging fruit that you can see that might lend themselves to immediate commercial application?
Yes, yes, Congressman. Sticking to your quantum computing specific point, you know, one of the three major use cases. I think the likelihood of there being a heterogeneous high-performance computer that has QPUs as part, underline the word part, of the architecture in conjunction with CPUs and GPUs, for it to be an accelerator to narrow down very large problems is actually something that could probably be designed into the next high-performance computer today. That's why I recommend that when you authorize the next high-performance computing program for the national labs, that you direct them to do that. The computer at Oak Ridge was the last previous one, Summit, was the first one that had two different types of chips. And that was proven, and it dramatically improved AI and general computing performance. I think it's low-hanging fruit to start taking a look at the chips that are going to be available in the next computing cycle to be included as part of a system. A fully quantum computer that has advantageous capabilities is I think, farther out, but I think as part of a system, I think that's low-hanging fruit.
Thank you. Yeah, that's encouraging. Dr. Edwards, I really respect the role that you have here on this panel, because you are dealing with an education very near, a situation very dear to my heart, which is education. I think the problem is bigger than the one that we're confronting here. I mean, we've got China has passed the number of passed the U.S. the number of PhDs in computer science that they have awarded a couple of years ago, and within the next year or two, they'll award double the number that we award. So our problem, I think, is broader than just educating students in quantum computing. I think we don't have enough students in STEM in general and computer science in particular. How do we solve that problem?
So this is a very big question. So maybe I'll keep my remarks
Well,
brief.
you've got 21 seconds.
I'm happy to answer also in writing. So quantum information science is more than just quantum computing. I think we all know that. And there are near-term technologies as well as far-term applications that you spoke of. It's a convergent area that spans all of STEM. So it's an opportunity akin to the space race, an opportunity to take this moment to inspire students and to inspire the current workforce to build up public literacy and to unite across all sectors to address the critical challenges you talk about. It can't fix all of STEM, absolutely not, I don't say that. But I think that we can use the NQI reauthorization and continued federal investments to build up the infrastructure to take a next step forward. And again, I'm happy to provide more detailed remarks in writing. Thank you so much.
We'll follow up. Thank you to everyone. I yield back.
Gentleman's time has expired. The chair now recognizes the gentlelady from North Carolina, Ms. Foshee, for 5 minutes.
Thank you, Mr. Chairman, for holding this committee hearing today, and thank you to the witnesses for your testimony and for appearing before us this morning. I am proud that in my district, North Carolina's 4th, indeed includes the Duke Quantum Center, a partner of the Department of Energy-funded Quantum Systems Accelerator, one of 5 quantum information research centers in the country. Mr. Debarr, the Department of Energy Quantum User Expansion for Science and Technology Program, or QUEST, was first authorized in CHIPS and Science to match researchers with existing commercially available quantum computing capabilities. Should the next phase of the NQI be expanded to include quantum computer user facilities? I understand from reading your testimony that you have some recommendations for this program in the context of the NQIA reauthorization. Could you please elaborate on those recommendations?
Yes, yes, Congresswoman. So I think there's 2 potential things, as you mentioned in your question. The QUEST program, which allows computer access for all researchers and develop computational scientists in the quantum algorithm space, that was authorized in the CHIPS Act. I highly recommend that get even more accelerated, or you consider that. Taking that up to $50 million a year is something I would recommend, which is a little bit of a bump from the CHIPS Act. Getting broad access to quantum cloud capabilities that researchers at universities or schools all over the country, I think would be a great use for development and research. And then I would also, as I mentioned previously, recommend a concentrated effort to building the first heterogeneous high-performance computer system at one or more of the national labs as part of the next big supercomputer effort, similar to what was announced here recently by DOE and some private companies.
Thank you. And Dr. Edwards, although I understand that many quantum technology jobs require extensive post-secondary education, there are also many roles that only require an associate degree from a community college or a trade school. Can you discuss what the skilled technical workforce looks like for quantum and how we can enable affordable educational opportunities for people to train for those jobs?
So for the second part of that question about how can we enable affordable training, I think we need to develop the curriculum that was referred to before. There are some initial strides that have been made possible by investments of the initial 5 years of the NQI Act, and it needs to be modular to be able to be deployed in community colleges. We need community college consortiums. I know there's several of them working to model after the Photonics Initiative. To build up capacity or capability at the technician level. For the actual skills needed, I actually would like to maybe ask Dr. Mertzbacher to.
Coming there.
Oh, excellent. I was going to say, I think she can provide more depth on the initial understanding of what skills are there, but to underline that this is all happening in real time, and we don't have enough data yet. And so I think building on what maybe Dr. Mertzbacher will say, we need more. We need to know more in order to design these programs for the populations you're talking about.
Thank you for that. So Dr. Mertzbacher, if you would, please.
Yeah, I'll add to that as well. My organization has a number of standing committees like this. One is the Workforce Committee. It's very active, and it involves members who are both in the education business, but the industry members. And we asked them, do you have jobs that are being done in your company by a PhD that could be done by a technician? And they all said yes. So there's a huge opportunity here. And I was talking with actually someone from your district about this. He said, we don't have as much trouble hiring PhDs as we do technicians. So we're doing a workshop this year to get more understanding around this. I think it is a very diverse ecosystem, and companies have different needs when it comes to technicians. But a technician doesn't need to have a quantum in front of their name. If they understand how to use vacuum systems, how to run electronics, how to keep things maintained and operating, they can be qualified. So what we need is to sort of get them quantum comfortable and appreciating the opportunities, and then helping to connect. A lot of times technicians don't necessarily relocate across the country, and so there's a difference in the education at that level, but it's equally important.
Gentlelady's time has expired. The chair now recognizes the gentleman from Tennessee, Mr. Fleshman, for 5 minutes.
Thank you. I thank the chairman and the ranking member for having this hearing, and to our distinguished panel, thank you very much. Secretary Debarr, it was a privilege working with you in the last administration. I'm glad that we could continue to work together, but to each and every one of you all, thank you so much. So you know, I represent the people of the 3rd District of Tennessee, which encompasses the entire Oak Ridge Reservation and all that it entails, including our great national laboratory. If I may, the main goal of the National Quantum Initiative Act was to accelerate development of quantum information science and technology applications in the United States over 10 years. Since the law passed, we've seen major advancements in technology, which has led to significant federal and private investment. Last year, Chattanooga's utility, EPB, launched the EPB Quantum Network, which is the first industry-led, commercially available quantum network designed for private companies, government, and university researchers to run quantum equipment and applications using EPB's fiber optic infrastructure. And while we still need to continue our quantum research and development activities, I think we have a real opportunity to jump to the next step, which is connecting the science to specific application areas. I'm interested in the panelists' thoughts, taking a regional approach to this, one where the key players in the region would form a consortium to create a test bed where one could take advantage of everyone's strengths and focus them on specific applications. Using East Tennessee as an example, you could take EPB and its network, bring in the Oak Ridge National Laboratory with its expertise in exascale and quantum computing, maybe some business and universities, and focus them on applying quantum science and technology to securing the electrical grid. My question for the panel: do you think a regional approach like this might lead to accelerating scientific discoveries and translating them into real-world applications? And I think we can begin with on this side and move across the panel, and I thank you all.
Thank you for the question, Congressman. Let me just start by saying that the U.S. government is taking protecting our networks extremely seriously, and NIST has been leading a standards competition for quantum-resistant cryptography, and the government is working to deploy that as fast as possible. That does not require quantum technology right at the beginning. In the long term, where we look to quantum networks, hopefully connecting our quantum computers and sensors, we're very fortunate in the government to have a lot of expertise in the agencies, and we've brought them together to make recommendations for you through various reports. One of them is a quantum networking report. The key thing is to focus on the hard technical challenges. One thing we really need are very high fidelity components to connect different types of qubits to enable a network. If we can do that, if we can solve that science problem, we can make everything the industry wants to do much easier. And I think that's maybe very well focused and compatible with regional teams focusing on these core transduction components that can go into those networks. If we can solve those problems first, then everything else becomes much easier. And I would encourage, this being a science-focused initiative, the government can really accelerate that hard piece and make it easier for all the applications thereafter.
Thank you, sir. Secretary Debarr. Congressman, the Chattanooga effort with Oak Ridge is a great example of the capabilities and prospects of regional efforts. Almost by definition, if you're going to build a network, it has to be regional. And so Oak Ridge in East Tennessee is at the lead. There's others, New York, Chicago, or other big areas of the country where things are being tested. The CHIPS Act authorizes certain aspects of that. I would recommend that this committee look to enhance that, because that's the way that things get built out. Once again, going back to the internet example of 1969, that's how the first four nodes of the internet started, and I think that's where we're at with quantum is to do the same. Thank you, sir.
I agree that regional efforts are very important, bringing people together to work together in ways that can only be done if people are close by. On the other hand, with the technology that's here, being able to work across the country is really important as well. And for example, we at NASA worked with people at Oak Ridge National Lab to support Google's quantum supremacy experiment. And so being able to do cross-country collaborations is also important. So balancing those things is critical going forward. Thank you.
The
Thank you.
gentleman's
We're
time
over
is.
time. It is, okay. I guess I have to yield back. I was going to ask the others if I might get at least a 10-second response, Mr. Chair.
Yes, Cardinal. 10 seconds each.
Thank you.
I just want to say that EPB is a member of my consortium, very active, and I visited them in March. We held actually our meeting there so that we could go and visit. I think it's a great model. I think quantum expertise isn't all consolidated in regions across the country. So if you want best in class, you're going to have to kind of break that open a little bit.
Thank you.
So I think that building infrastructure to have regional hubs in areas especially that are quantum information deserts is critical, and I think it aligns with the notion that our educational systems are local and locally governed and provides on-the-ground access, or could provide, if we were successful, on-the-ground access for people of all ages to have a front row seat I was talking about.
Thank you. I thank the chair's indulgence. Mr. Chair, I yield back.
Gentleman's time has expired. The gentleman from North Carolina, Mr. Jackson, is recognized for 5 minutes.
Dr. Tahan, I want to follow up on the answer that you just gave to Representative Fleischman's question. I'm very interested in trying to verbalize for my constituents the gap between the state of the art and practical applications, and I really don't know if that gap is more about scaling up existing technology and finding something that's affordable, or whether there are huge technical problems left to solve. It sounded like your answer was that the biggest thing the government can do is help solve a particular technical problem, and that was the limit of my understanding. So am I right about that?
Well, this is a pretty broad field. It depends on the category. So there's computing, networking, sensing, right? For networks, the point I was trying to make is that there is a classical solution to the risk of a far future quantum computer that the government is working to deploy, to standardize and deploy. There are opportunities for quantum-enabled networks to do more, and that's more of a research and development thing that we need to solve a lot of problems to solve. So that's for networking. For computing, the question of applications is always, has been the most important one. We've taken the last 25 years to build very small research-like computers, 100 qubits, just starting to be at the point where we can't simulate them on our laptops or even on our supercomputers. But we don't have applications to run on those things yet that do anything useful other than science and trying to understand how to build bigger computers. We don't know when quantum computers, at what scale, they will start to be actually useful, like generating Nobel Prize science or commercial applications. It could be in the next 5 years, it could be longer than that.
I want to drill down on that exactly. So the state of the art is roughly 100 qubits, is that what you're telling me?
Hundreds. IBM announced a 400 qubit machine, but we're sort of in the hundreds. category now.
Okay, and we really don't have a working theory as to what level of qubit is going to unlock some practical
No,
applications?
we do. So over the last 20 years, we've developed algorithms, proposed algorithms that do useful things. One of them is cryptanalysis, which is a negative thing we need to protect against, so good break codes. Another is chemistry and materials discovery. Those algorithms that we can cost, meaning we know exactly how many qubits you need, the estimates are around hundreds of thousands to tens of millions of qubits, okay? But there are other proposed algorithms that are more heuristic, kind of like deep learning based, that we cannot, with mathematics, prove will work until you build the machine.
Okay.
So the goal is we need to build bigger machines and see if they're going to work or not.
Okay, so you think we've got some practical applications at the 100,000 level, but we may be some practical applications short of that, but we really don't know yet.
Exactly.
Okay. Between the 100 qubit level that we're at, the state of the art, and 100,000 qubit, what's the biggest technical challenge? And
Scaling up, how to control all those qubits. Each one of those qubits is like a little very sensitive animal that you need to touch all the time. You need wires or lasers that go down to it. So unlike your classical computer, which has 10 billion transistors but only 1,000 wires, a computer with 100,000 quantum transistors would need hundreds of thousands of wires. So that's the big technical challenge.
So, Congressman, probably as early as later this year, we might have a 1,000 qubit chip out there that's capable. And how the equivalent to architecture of high-performance computers with CPUs and GPUs, we don't have a GPU chip the size of this room. It's a bank of chips, as you know. And so the likelihood of taking a 1,000 qubit chip and starting to network them, maybe 3 or 6 in one cryo chamber, so you can maybe get to 6,000 qubits. And as was announced recently, as part of a bigger high-performance computer with CPUs and GPUs, 100,000 might be able to provide an accelerator function to dramatically improve that high-performance computers.
All right, I just need to understand, is there a breakthrough that hasn't happened, or do we have the science and now we're just scaling up?
Okay, I might jump in here.
Please.
We don't know yet how to build such a machine. There are roadmaps from several companies, but it hasn't been built yet. And the physics, the ability to control this many quantum objects all at once to do computing is of course critical, and we will get there. But there are massive engineering challenges as you try to scale this.
Name one.
So in the atomic, there's multiple platforms. We don't know which qubit is the best qubit. There's superconducting qubits, there's semiconductor qubits, there's atomic physics qubits, both ions and neutral atoms. There's a number of different ones of those, and we know how to get to 100, but the challenges is like Dr. Tahan said, the challenge is connecting all the wires. In the atomic physics case, it's using all the lasers. And we often don't have we're operating on the edge of what's possible. And people are right now in industry often inventing solutions to be able to circumvent the necessary amount of wires, or to try to reduce the number of lasers you would need to control that many quantum objects. It's a really hard problem, and we will get there, but there are significant, I don't know if they're necessarily physics breakthroughs, but there are engineering challenges that have to be co-developed with industry in order for us to succeed at building this.
Gentleman's time has expired. The chair now recognizes the gentleman from Georgia, Mr. Collins, for 5 minutes.
Thank you, Mr. Chairman. You know, the discussion that we're having today, I think, is about an area of science which probably very few of us really understand. You know, Albert Einstein himself kind of struggled to put his mind around this, and he was often quoted as saying, if the quantum theory is correct, it signifies the end of physics as a science. So he clearly had mixed views on the subject. So my question is to any of the witnesses. What would you tell a Georgian in my district if they ask why the government should be investing billions in quantum research, and how is it going to impact their lives?
Maybe I'll start out by saying it's already impacted their lives. You know, if you think about the global positioning system, what helps us get home, that's estimated to be $1 trillion impact in our society. I mean, it saves me every single day from a lot of traffic. That is based on quantum clocks, or quantum, a version of a quantum sensor. Magnetic resonance imagers, brain imagers, are based on our understanding of quantum physics. The next generation brain imagers, if we can really bring some of these ideas from lab to market, could be around your neck. Instead of having to go into a big tube to see if you have a tumor, you could be monitored all the time, or much more less invasively. Think of what that could do to broaden healthcare to the world, right? So we can bring these over the market, but we need to keep our eye on the ball on the applications that could actually affect society and carry it. And that means bringing other agencies involved, investing in industry to make it happen.
All right. Congressman, I just want to highlight the biology imaging point. The prospects of moving from an MRI, which for lack of better description, comes up with a blob, right, that you see, and you still have to do biopsies, and it has to reach a certain scale of the cancer, for example, before you can even see it. The prospects of, and NSF's been funding some of this, of a higher end, either magnetic or other type of quantum imager, to go to the individual cell. And so if you could capture and visualize the first cell that is cancer and it moves from your thyroid to your pancreas, not wait until it turns into a tumor, that's the possibility. And so the possibility of catching something that early with a piece of quantum sensing will remake medicine. And so that's a prospect.
Good. Hey, I know maybe I had another area that I really wanted to get into real quick, and I appreciate your answers. That really makes it easier when we're talking to our constituency. We just penned a letter, Chairman Lucas and I did as subcommittee chairman, to the NSF about China and Berkeley and how they were receiving money from the Chinese and money from the federal government on research, semiconductor research, and how they were conducting tours of these research facilities for the Chinese. And that's very concerning. I know we've been talking about that here this morning. I also had the opportunity to speak to a group not too long ago about quantum technology. And my question is for Ms. Mertzbacher and Ms. Edwards. Thank you for the good Southern name down there. Easy to pronounce. When I was talking to them, they mentioned the fact that we need to keep these visas for the Chinese coming in because we don't have people that have the education to help us with quantum technology. And that worries me. And so from an education standpoint, Ms. Edwards, is that true? Do we still need to make sure that we have visas coming through for the Chinese? And Ms. Mertzbacher, the workforce, you indicated in your opening statement, upscaling existing and upcoming workforce. And I would just like some comment on that so that we don't get into the same situation that we have now with the semiconductor research.
So I admit I'm not an immigration expert, but I do recognize the challenges of national security in this space. And I do think that, aligned with the recommendations that came out on Friday, it is actually important, especially at the graduate level, for us to continue to draw on the international expertise and the domestic expertise that's available. We need to simultaneously build the domestic workforce, and that is a major, major gap. And we should not get distracted from doing that. But it is really important to recognize the contributions internationally that colleagues across the world, including China, have brought, and that they work in our labs in academia. And I think this is incredibly valuable. And there are recommendations that Dr. Tahan can speak to more directly about this.
Gentleman's time has expired. The chair now recognizes the gentlelady from Ohio, Ms. Sykes, for 5 minutes.
Thank you, Mr. Chair, and thank you to the panel for your time with us. This is certainly a very interesting and important conversation. One thing I've probably said in this committee and otherwise is the best part of this job is learning about a lot of fascinating pieces of information, technologies, professions, but I also wonder how I would ever know about those things if I were not a member of Congress. And it frustrates me as much as it encourages me to learn about these things. And I wanted to go back to something you mentioned, Dr. Tahan, about the people being the most important part of this equation. And none of this technology works without people who truly understand and know what's going on. And when I think about the people in my community in Ohio's 13th district and what do they actually know about quantum technology and how do they get involved in quantum technology, and is it just something that they've seen or heard the term on TV but it's not for them? So I would like you to dive a little bit more into what are the opportunities that we can do to connect the dots to our constituents and members of our community who are not familiar with it, and then start talking about the pipeline to get them involved and employed in this.
Yeah, a pleasure to answer this question. It's something I'm very passionate about, just looking at my career, how I got into science. And to me, it comes down to there being careers, for parents to want their kids to go into, and then educating, inspiring, and giving experiences to people. So what we have done is try to use the White House to amplify the great efforts that are already going on at NQI. World Quantum Day, we've tried to make into a big event where we have, famous people, frankly, give videos about quantum. We've, with Emily's and other people's help, we've brought quantum modules into hundreds of schools across the country. And that's 100 schools times 30 students. So we're getting people a taste of this is really cool. It's a great career. Many people can be successful in it. And now it's our job to even, how do we scale that even more? And that's really what we're talking about, having a center, having more coordinated activities to really bring this into living rooms and not just the New York Times op-eds. That's what we really need to do.
Well, thank you for that. And I also appreciated your comment about moving this beyond the top 25 schools within the country and allowing other universities. And I believe that was you, Dr. Edwards, who has a degree from Appalachian State. And again, thinking about how do we get people who are a part of tech schools, trade schools, state schools, involved in this and not feeling like they just have to be Ivy Leaguers to be a part of this conversation. And in reading your testimony about your K through 12 curriculum and encouraging more people, if you could share a little bit more about the work that you have been doing and that you can continue to do with the right support from people like us.
Thank you for that question. I would like to say that, acknowledge that the work that I've been doing is a work of an incredible group of people, and that really I'm just providing a conduit to share what's going on. And so what we've been doing, and my colleagues at University of Chicago and University of Pittsburgh have worked very hard to pull together teachers to build a quantum information science framework for introducing quantum into high school chemistry, high school physics, computer science, math, as well as middle school. There's also a public elementary school in Philadelphia that we've talked to that we don't have anything for formally for elementary school outside of the activities that Dr. Tahan mentioned, but there's a school there that's actually experimenting with having a science lab focused on quantum in the elementary school that students have exposure to. And so the framework that we're developing is agile, and the next step is curriculum. So what needs to happen is a center to build on the steps that we've taken so far. There needs to be a national resource to develop curriculum, to connect these different parts of the pipeline, to work and build upon the data collection that the QEDC has supported, and to really build up robust programs and make sure that they are effective, and again, address these information deserts that exist widely across our country. And so we've been working on it, but we need a center or something to build on this partnership, the Q12, that's currently voluntary and supported with limited funds from NSF for a short period of time.
Thank you so much for that. And with my remaining time, I'll just express one part that I just don't hear often in here and would like to hear more of is the fact that representation does matter. The fact that we have 3 women here on the panel is incredible. It would be great to see more people of color as we're trying to find the missing million technology workforce that is not here. And if you can see it, you can be it, and you can believe it. And as I sit across from Eddie Bernice Johnson, it is a reminder to me that seeing someone on the wall that looks like you allows you to see yourself in these positions. So thank you for all that you're doing, and continue to be good representations of what it means to be a woman in STEM. Thank you, and I yield back.
Thank you, Ms. Sykes. Gentlelady's time has expired. The chair now recognizes Dr. McCormick from Georgia for 5 minutes.
Thank you, Mr. Chair. So what an esteemed presentation today. So many educated people. I'm really excited. One thing that caught I had a bunch of questions asked from a bunch of people, but right off the bat, I want to address Dr. Mertzbacher. Am I saying that correct? You said something very interesting during your presentation. You said that we're not getting the same investment from the private side of the world that we used to have, and that's kind of tapered off, and that's why it requires more government investing to continue the leaps, if you will, in technology in this. Can you tell me why you think it is that investing in quantum technology is decreasing?
Well, it actually isn't decreasing, but the growth has slowed. Important difference. So when you look at the growth, it's not as fast as it was, and that could be for a number of reasons. It could just be that there was sort of an initial spike and things have sort of tapered off a little bit, but there still is strong investment taking place. You know, look at the tech economy. It's an economic situation that may be influencing or impacting this. That could be temporary. I think there's high risk, and there's a lot of hardware problems that we heard about today, and those are not the typical VC investment opportunity. And so these are all reasons why I think that there really are areas where government has the opportunity to step in, de-risk, bring things a little bit farther along, and then the private sector will come in when they see a business case, but they have to see that business case. And I will just point out that we haven't said the word supply chain yet here, but there is a supply chain that's critical and has some special components for quantum systems. And those companies are sort of looking around and they don't see the markets today. So there's a chicken and egg problem. So whether they're using their own R&D funds or looking for investors from outside, that chicken and egg market problem is where we are right now. That's
what kind of concerned me a little bit, just from the standpoint of, that surprised me when you said that, considering what's going on with AI and the private investment in AI. You're right. Once the seeding money is there and we see it start to bloom, it's very unusual to see somebody stop with the investment from the private sector if they see something that's really forward-looking and visionary. So I just thought that was interesting. I'm not sure we want the government to continue after the seeding money. I like to see the free market just kind of go with whatever it's supposed to go with. So I'm thank you for that remark. Dr. Rafel, I wanted to really quickly, I just went to SAS in Luxembourg and was looking at all the different orbital systems and stuff like that. I know that one of the things that we talked about recently was that the NASA aims quantum computing and the way it tracks orbits and space debris and everything else like that. What is this technology going to be used to take that next step in this huge, vast universe of debris and satellites and everything else like that? In the way, is it going to have a direct application in tracking this immense population in the inner and outer space?
We believe so. The extent of that is still a research question, but there's quantum sensing technologies that can help with that. The other thing is that there are huge computational challenges there. We also need to get the data back. There's more and more data, which is super exciting, but we need to get that back. And so doing data compression and the like can be super helpful there as well. Lots of possibilities here for quantum computation in those areas. As was mentioned before, this is a heuristic area for the next few years, and that means we don't have pencil and paper proofs yet, but the technology is just at the point where we can do things on the processors that we can't do in simulation, and so the next 5-10 years are going to be super exciting on that.
Yeah, it's crazy to think about how complex the calculations get when you're in a 3D universe and you're talking about the vast space that we have to compute as far as deconflicting. My final question, Undersecretary Debarr, how do you think the regulatory burden is going to affect both the development and with the guardrails on future technologies in the quantum space, as far as where do we draw the line? You know, controlling the process of leaking out information that could be harmful, or developing processes that could be harmful versus developing stuff that can protect us. How do we regulate as congressmen and women what we're supposed to do in the future?
Yes, Congressman. So as I mentioned earlier, I'd recommend the DOE risk matrix for technologies as a screening mechanism that not only DOE but other agencies could use, that they can green light certain open science topics, and we're like, okay, but we're consciously knowing what's okay, and then identifying what type of technologies should not be engaged with adversary nations.
Well, we'll look for guidance on that. Thank you. With that, I yield.
Thank you. The gentleman's time has expired. The chair now recognizes Mr. Frost from Florida for 5 minutes.
Thank you, Mr. Chairman. So even experts in quantum computing see their field as a mysterious, complex, and full of surprises. But one thing is clear, that this is a powerful, revolutionary technology on a historic scale. Dr. Rafel, did I say that right correctly? Rafel. Thanks to NASA, industry, and research being done at the University of Central Florida, Go Knights, that is in the Florida's 10th Congressional District, rockets are sending science experiments into the skies above my district all the time. You've discussed how NASA conducts research, including basic quantum physics to understand quantum mechanics and general relativity. What are the unique benefits of the International Space Station for quantum physics experiments?
So we're able to do things up there that are unprecedented. Just as one example, it's the unique place where we can get Bose-Einstein condensates and explore that. I also just want to go with some of what you've said there. This is an incredibly exciting area. It's also one that none of us totally understand. I think critical for building up the workforce is to have people be super excited about working in areas that they don't totally understand, and that those mysteries there will really help us go further in that area. There are a lot of NASA areas like, do people really know what a black hole is? But people are super excited about that. Let's do that for quantum information sciences as well.
Dr. Debarr, where would quantum computing research be in the United States if federal agencies and funding had not provided the infrastructure that you've spoken about today?
Yes, Congressman. High-performance computing, and quantum is a subset, quantum computing is a subset, would not anywhere near be placing the U.S. in a leadership position without federal investment. The first high-performance computers, the number one, next high-performance computer is always developed by the federal system, namely the DOE National Lab. So the current number one is at Oak Ridge. The previous one is at Oak Ridge. The next one will be in Illinois. Right now, you won't see commercial customers paying for the very high-end next chip. It has historically been the national labs, as well as NSA. So that's the only way that the next stage, and it's been a tried and true method of accomplishing that.
And Dr. Tahan, what would you say would happen if these investments did not continue?
If you look at the history of quantum computing, it was the government's seed investments in building the technologies that enabled the 100-qubit machines we have today, right? Industry is mostly focused on integrating what's already been discovered into trying to make something useful that they can provide their customers value with, right? So if we stopped government investment, all the new inventions that would enable the 1,000-qubit, the 10,000-qubit systems would be much less likely to be implemented. And as Paul said, the draw of a customer would be lost, an important customer. So, I mean, it's really critical that the government stay engaged and make sure that we're still leaders.
Yeah, I mean, it's good to know that federal investments can really serve as a broader investment to attract private funding and spur innovation in the country. And to any one of our witnesses, I wanted to give anybody the opportunity to bring up any suggested improvements in the National Quantum Initiative Act that hasn't been mentioned yet.
I'd just like to mention, once again, we have international allies and partners that are vital to growing this ecosystem. Quantum is extremely broad. We can't investigate every part of phase space, and we also need a trusted supply chain with countries who we trust. right? So we need to follow up on our international cooperation statements by having some kind of joint fund to push those forward, independent of everything else we're doing in the U.S. I think that would be really beneficial.
Just to highlight that authorization from the act to allow for what Charlie just said, to allow the agencies to know that you say it's okay, I think is key. At DOE centers that happened in the first NQI, we have at Fermilab, we have Italian cooperation. And what was just announced at University of Chicago in terms of the big quantum computing effort, Japan is now really the second most powerful high-performance computing country in the world, is a part of that consortium. So I think any authorizing language which makes it really clear the agencies know they have authority to do what Charlie just said would be a great line item in a bill.
Good. Thank you so
Gentleman's
much.
time has expired. The chair now recognizes Mr. King from New Jersey for 5 minutes.
Thank you, Mr. Chairman, and thank you to all of our witnesses for being here today. Dr. Mertzbacher, in your testimony, you highlight several key areas to explore, utilizing quantum solutions to solve some of our greatest challenges. I'm particularly interested in hearing more about the possibility to improve biopharmaceuticals, particularly when it comes to drug discovery and personalized medicine. Could you please elaborate on how quantum computing and modeling may help advancements in this field?
Yeah, thanks for that question. The application to the pharmaceutical industry is one of the areas of high interest on the industry side, and I think it will leverage some of the benefits of quantum computing for being able to optimize and streamline search problems. Today, the way that drug discovery happens is there's a huge wide net cast, and then there's a very expensive and long process to winnow that down to find one drug, maybe. So there's a lot of opportunity to improve that process, to make it more efficient and take less time. The pharmaceutical industries all the companies are hiring people who have enough knowledge about this field to start exploring the application of quantum computing in their business. There's actually a consortium that my group works with that's focused on life sciences, and all of the big companies are there, and they're actually talking quite a lot about what they're doing because it's still early stage. But I think there are real opportunities, and that's an example of one where the communities can come together and educate each other. The pharmaceutical industry needs to say, here's what our problems are, the kinds of challenges we have, and then the folks who are doing the development of the software and the hardware can more quickly develop the tools for addressing that.
Thank you. Dr. Tahan, telecommunications is key to our society, and having a strong and resilient telecom infrastructure is critical. From broadband to 5G rollout, optimization after emergencies, and keeping our systems up and running, the telecommunications sector faces a wide variety of challenges that could benefit from quantum technologies. In fact, the Presidential Advisory Committee on Communications recommended a quantum sandbox program for developing applications that could benefit communications resilience in a report released on May 2021. Applications are already being developed in Europe, but not yet in the U.S. Can you please tell this committee how the U.S. government will engage with the quantum industry and research community to help utilize today's technology for telecommunications, both quantum computing as well as quantum communications?
Yeah, I'd be happy to, Congressman. I think there's two ways. One, as the country moves to upgrade all our networks to quantum-resistant cryptography, there's a huge opportunity for industry because, one, agencies, organizations, companies are going to need help understanding what parts of their telecommunications infrastructure needs to be upgraded. Then they will need the new routers, the new software to actually upgrade them. I mean, this is going to be a very large, long-term upgrade cycle. It's a great opportunity for industry. The second part is, as we, hopefully through the NQI, start to build quantum network test beds to prove out and find the applications for new types of networks that involve quantum mechanics, hopefully there will be opportunities to build the core components that go into those networks and make them actually reliable and robust And I think there's going to be a lot of spin-off applications for other parts of telecommunications as well, low swap, frequency modulation, and so on, that can impact even classical technology. So I think those are the two domains where there's real opportunity.
Okay, and my last question, Princeton, while it's not in my district, it is near my district, leads one of the 5 DOE quantum centers, and the university is leading in this field. Princeton's work to expand the quantum information science ecosystem includes participation in annual quantum career fair, quantum summer schools, internships, training for young researchers, and a unique summer research program in collaboration with IBM. I guess this is the question for Mr. Debarr and Dr. Mertzbacher. What recommendations will you have for these facilities and universities to build out their workforce? How do you recommend that we engage with physics and engineering departments, as well as with computer science and algorithm development disciplines, to build out this critical workforce?
Yeah, Congressman, I think, one of the things that can be done is actually start taking a look at specific technologies and applications that are attributable to different departments at universities and try to drive those with the experts of those universities in terms of developing them. I'll give you an example. There's a workshop being prepared right now on energy deployment for quantum computation and systems. So taking, for Princeton, plasmas for fusion, taking a look at modeling for that is going to be one of the breakout workout sessions on energy and discovery for quantum, and that's a direct example for Princeton.
The gentleman's time is expired.
I yield back. Thank you, Mr. Chairman.
The chair now recognizes Ms. Bonamici from Oregon for 5 minutes.
Thank you. Thank you all for your testimony and your expertise. There's a tremendous promise and potential with quantum technology, so thank you for being here. I was an enthusiastic co-sponsor of the original National Quantum Initiative Act, and I want to note that I'm very proud that Dr. Michael Raymer, who is from a physics professor from my alma mater, University of Oregon, played a role in shaping the initiative, and University of Oregon has continued, of course, to lead on the Pacific Northwest on this issue. So also enthusiastic supporter of the CHIPS and Science Act, which, as you know, really is building on quantum technologies. So Dr. Rafel, I really appreciated your excitement when you talked about how you don't all understand everything, and we want people, the word that came to me was curiosity. We want people who are intellectually curious, I think, to get those people and get them into the field. But I want to ask you, you underscored the potential for quantum sensing tools, including gravitational mapping and laser-cooled atoms to radically improve the precision of Earth measurements. I work a lot on climate issues, and I wonder, at what scale do these technologies need to be deployed to effectively measure trends like sea level change, dwindling freshwater resources, for example? And how can these technologies improve climate modeling as we rapidly approach the global temperature rise of 1.5 degrees Celsius?
We would like to see these widely deployed. As I mentioned, this gives much higher resolution, which enables us to understand these issues much better. And this affects all aspects of Earth science and potentially beyond. And I'll also just mention that curiosity is a wonderful NASA word. And I think for young folks and older folks, being able to address challenges while helping us investigate our curiosity will help bring the workforce to us. And it doesn't have to just be young folks. It can be a bunch of us had careers in something else because quantum information science didn't exist.
Didn't exist, right.
And so people should remember that they can come join this effort from their different expertise, including in areas that you mentioned.
I appreciate that, and as a member of the Education and Workforce Committee, I'm always thinking about the students who are in school today, the jobs that will be available when they're in the workforce might not exist today at all. So we have to spark that curiosity. So I'm going to address this to Dr. Edwards, but others can weigh in. I'm looking at policies, of course, focusing on research and development, promoting public-private partnerships with Representative Obernolte brought up, but also that workforce issue. So I want to hear about how we can encourage collaborations among private sector, industry, government, academia. But also, I want to follow up on the question that was asked about building the workforce and the diversity of the workforce. We have a lot of conversations about the importance of a diverse workforce and talent line when it comes to AI, for example. Why is that also important in quantum, and how can we spark that curiosity? I'll start with Dr. Edwards, and others can weigh in.
Thank you, Congresswoman, for this question. Quantum information science is so cross-disciplinary, and there's a lack, as you recognize, of diversity across any measure of diversity in the fields that contribute: computer science, chemistry, physics, math, electrical engineering, materials science, you name it. There is a persistent lack of diversity, which means we are leaving something on the table in terms of the American workforce. Quantum information science is exciting and sparks curiosity and offers us perhaps a once-in-a-generation opportunity to try to start at the beginning of a field, to bake in opportunities and build out infrastructure in deserts across the country that don't have necessarily access. And to really try to move the needle, because when we look at historically, if we ignore this until there is application and jobs, then the quantum workforce will look exactly the same as it does today. And we will be sitting here in 10, 20 years from now, and if I have the privilege, I'll be saying the same thing, and we'll be having the same conversations.
We hope we've addressed this. One of the articles I was reading talked about the importance of interdisciplinary education, and I think you touch on that. And my time's about to expire. Does anybody want to briefly mention the importance of the public-private partnerships?
Well, I run one, so I totally want to foot stomp on that idea. I come from a background, my previous job was in the semiconductor space, where I saw the magic that happened when industry and academia worked together and the students had exposure while they were a student in industry jobs and experience. Mostly when you're at a university, you're seeing the university world. And if you can get industry engaged with the academic enterprise, you get those students seeing life outside of that bubble, and it's hugely valuable for the students during their education. So
Absolutely. Thank you so much. I yield.
And I thank the gentlelady for her clever asking of the question with 0 time remaining. That is a skilled professional. We go to the gentleman now from Illinois.
I'm going to sit here and let the clock run out until I get to 0 and then ask my question.
You may not be as lucky.
Thank you all so much. Dr. Edwards, you had mentioned a little while ago about this question of how to get sort of high coherence qubits, and that facility you mentioned, Fermilab, is just at the edge of my district, and those materials that come from foreign countries all come in there. And it is of course true that we want to make sure that we preserve IP in the United States. I also think it's important to remind ourselves periodically that we have these amazing national labs that attract people from all over the world. And I would say it's actually a blessing that we have those international components there, because those people who know how to make those things have no ways to deploy them but at our national labs. Mr. Debarr, you and I were 4 years ago, I think, at the groundbreaking for the Integrated Engineering Research Center at Fermi, which is was just there a couple weeks ago for the ribbon cutting. I would say that they have completed the project as you and I intended when we dug those ceremonial first shovels. But that's a very intentionally international space, and so just let's not lose sight of that. I want to stay on the high coherence, and you had raised the issue, but I think you had mentioned that Dr. Tahan was the one with the expertise, so I'll turn to you for a moment. Can you give us a little understanding, because every time I go to visit the folks at Fermi, there's this question about how long can we hold these qubits in a predictable way, and what's the progress? And could you give us just a little understanding of both what the progress has been in creating coherent qubits, and what's sort of the benchmark we should be watching that says, yeah, once you can hold it for this amount of time, now we've really unlocked quantum computation in a reliable way?
I can try. Thanks for the question. I was actually just at Fermilab earlier this year. It's some really great team working on there just along these lines. If I try to simplify it in terms of the history, 20 years ago when the field started, coherence time of one of the best qubits was a nanosecond. Okay, now people at Fermilab, others are making 100 microsecond, even a millisecond. So we're talking about many orders of magnitude improvement. Where do we need to get to, right? That is a little bit of a more, so we're seeing dramatic improvement every year, right? It's a little bit more difficult question to say where we need to get to because it's a holistic problem. Like when you're trying to build a quantum computer, it's not just one number that you're trying to optimize. It's how hard is it to measure these qubits? How hard is it to control them? How fast can you do it? Because if you can do it faster, it matters less how long they live. How good is your error correction? But nominally speaking, we're approaching the time where you can start to devise systems that you can imagine one day could do something useful. Like at this sort of millisecond time frame, it's probably good enough to do error correction and build a big system, a lot of qubits, to run the algorithms that we've costed very well. The better we can make it, the better we can make the coherence, the easier, the smaller the system will be. So that's why you can't stop, right? You need to keep working on the disruptive new ideas, because if you can make these 10, 100 times better, then suddenly everything becomes much more feasible and much less engineering problems need to be solved. I hope that's useful.
Yeah, and I guess what I always struggle with when I go to Fermi is, number one, they're way smarter than me. That's a challenge. But number two, there's these sort of fundamental basic material science questions of how do you create surfaces with the appropriate atomic purity to keep these things going, and how much should we understand this as still a basic science challenge versus engineering? Because, I mean, scale up to me is an engineering challenge. Every time I go visit the lab, it seems like they're doing basic science. And I don't say that judgmentally, I'm just
Because, yeah, the way to think about it is, I mentioned coherence time as milliseconds, but if we talk about fidelity, like 99 times out of 100, the thing works, or 99.9, we talk about the nines a lot. We need 3 nines fidelity, 4 nines fidelity. Each extra 9 requires solving a whole bunch of material science and physics problems. So we can, and then you take the engineering to put them together to make a computer. So there's always going to be in quantum computing scientific and material science problems to solve all the way towards till when we have a quantum computer. We just have to embrace that. Just like in the transistor industry, every new type of transistor needs, thousands of people are working on material science problems to get that next generation.
So I have 3 seconds, and I want to respect the chair and not do what he just criticized. But Mr. Debarr, I'd love to follow up with you afterwards in writing. You and I talked 4 years ago about sort of pacing out these quantum networks and what that would take, and I would love some update for you. Maybe we can follow up offline about what it's going to take to start building those out, because it still seems revolutionary and it still seems like tomorrow.
I'm glad the Congressman. Illinois and Chicago area has made dramatic progress since NQI was passed 5 years ago. It's hard to describe it even in 5 minutes.
I'll take that offline. Thank you. Yield back.
And now, the lesser questions will come from me. I don't have a university in Illinois, but I do have the University of California, San Diego, and we're proud of the work we do. Some of my questions, though, I think are going to be monetary. Mr. Secretary, I'll start with you. And I want to give everyone a chance. We talk a lot about diversity. We talk about spreading out. But then we also talk about the cost of this rollout. Now, we're rolling out something that, quite frankly, you said it very well, it's a mixture between lab and production. The Manhattan Project wasn't done in every university in the country for a reason, not just the sensitivity of the material, but the need to concentrate the brain trust in that work. How can we see when we're competing against China with over $15 billion of direct support, and they clearly concentrate, even India concentrates among relatively few universities, the best and the brightest. From a standpoint of the move forward, how can we balance that rather than spreading out our money and make sure that we are concentrating those fields of excellence? And then I have a follow-up.
Yes, Congressman. So I think I think the federal system does it well, and I think if we just kind of continue with that, you have entities like NSF that are very good at single researchers at a university doing a project, including in quantum, and having a broad base, much of which was discussed. And then periodically you have highly concentrated efforts, because you do want to have some highly concentrated efforts to build something. So let me take Southern California. Caltech, San Diego, University of San Diego, JPL, Santa Barbara, Google, also in Santa Barbara, UC Santa Barbara, as well as Google in Santa Barbara, are at the precipice of building a quantum network. And if funding kind of fully comes through, authorized underneath the CHIPS Act, I think that the prospects of doing that is relatively straightforward. So I think there's a balance, right, between the different sort of systems, individual principal investigators, and let's go build some systems. And I think in this area, we're ready, including Southern California.
Okay, and I saw a lot of head shaking, so usually it's a good sign.
Yeah, I agree. This has to be an and, not an or. You know, we cannot give up our scientific excellence by expanding. We need to also expand. But I think in terms of expanding across the country, we're really talking about not these huge mega efforts to build and focus developed systems integration, solve these systems integration challenges, but developing smaller systems that can be used to train up the talent for those people that can contribute to those big effects.
Okay,
This hub-and-spoke model can work quite well.
Well, and perhaps you can be my visionary or others on my follow-up question. Going back generations of computers, when I was in college, we put paper into NCR 500s. We wrote our programs. We were learning, but we were learning at a very rudimentary level. By the time I was a lieutenant running a deck facility, we were a hub for all kinds of places because our processing capability was available through those high-speed 2400 baud super dedicated lines of the day. But ultimately, it didn't matter what the connection was. They had access to our large capability that we had within a very expensive facility. That hybrid system, which eventually became the internet, where universities had access to what was a military facility and vice versa. We could reach out to them for development. How do we take quantum, get the most bang for the buck by leveraging what one might call hybrid, the existing technology, the existing computers that can help reach those but not overburden them, or at least maximize the benefit of them?
Yeah, well, we are very fortunate in our field that the internet already exists, that cloud computers already exist.
I'd heard that.
So people, have been hooking up their quantum computers to the internet, providing access, and the Quest, bill that was authorized in the Science Act would expand that access to more subject matter experts who actually are experts in chemistry and materials. We need to bring the domain experts to be able to use those machines across the country.
And so
anything we can do to do that will be better.
Yeah, my follow-up question for the record now will be for each of you. If you could give the committee, myself, as much of your vision of how we leverage these areas of excellence, in other words, where we invest in research facilities, but where we invest in facilities that can be that hub and spoke to the rest of the universities, so that no young, bright mind will be left without the ability to reach out beyond. If you're sitting at Kent State University, you're likely not to be the hub, but if you can have the spoke that leads to that hub wherever it is. So if you could give me your vision, because our investment might best be in making those tentacles much better than they are today. I am concerned that we all take credit for the internet, but the reality is, what have we done to make it better at reaching out to this new quantum world that we're going to be in? So if you would each give that for the record, I would appreciate it. And with that, I go to the gentlelady, Ms. McCullen from Virginia.
Thank you, Mr. Chair. Good afternoon. recently I was able to visit the Thomas Jefferson National Accelerator Facility in Virginia, which, as you know, conducts groundbreaking nuclear and particle physics research. Recently, their engineers were able to use an innovative photon detection system to solve challenges in quantum computing, quantum sensing, and quantum cryptography, which is one example of the potential for quantum information science to help us solve previously unsolvable problems and better understand the fundamental building blocks of matter. So I look forward to hearing more from you today and in the future about how Congress can support the advancement of quantum information science on behalf of society. But my first question is, computational models are essential to our understanding of the mechanisms driving climate change and the impact of efforts to mitigate climate change. These models are highly complex and computationally demanding, making climate modeling an ideal application for quantum computing. So, Dr. Rafel, could you discuss how Congress can support the development of quantum computing for climate applications in a potential National Quantum Initiative Act reauthorization?
Thank you. Yes, there are many computational challenges in climate and earth science generally, and quantum computing has the potential to really affect how quickly we can compute those things, reduce the energy with which we can compute those things. We also have quantum sensing, which can help us understand better ice, oceans, land mass, and changes. So the applications in those areas are broad, and to tie in with some of what we've talked about before, bringing in folks who have expertise in those areas and tying them tightly with the folks who have expertise in the quantum computing area, and really understanding what really specifically are the computational challenges in your areas that will really make the difference. And we're working on that at NASA, but I think more broadly, having those computational challenges would be great.
Thank you. The advances in quantum computing put our traditional forms of encryption at risk. So with serious national security implications. And my understanding is that some agencies like NIST are already working to develop a secure post-quantum encryption techniques. So Dr. Tahan, could you speak to OSTP's work to address the national security risks posed by quantum computing and what support you need from Congress?
Thank you, Congresswoman. I'll just start by saying I went to William & Mary, and I know Jefferson Lab quite well. We've been doing a lot to support the transition to post-quantum cryptography. Probably the most important thing that has happened in that space in the last year is the President signed a national security memorandum, NSM-10, on quantum computing, which lays out clear objectives for the agencies to, in a timely and equitably manner, move the whole nation to quantum cryptography. So it's going to be expensive to upgrade all the routers, to understand what needs to be upgraded, not only in the federal government, but also in our small businesses and companies across states across the country. To do that, we need to know what we need to do. So first and foremost, this process included OMB and included the agencies like NIST, DOD that have significant equities to make that process. And that's being run out of National Security Council, and we could help facilitate interactions with them if you want to know more.
Thank you. And in the time left, providing students with the hands-on quantum research experience is expensive, and availability is limited at many institutions, as we've discussed, including at many HBCUs and minority-serving institutions. So, Dr. Edwards, how can we ensure that all students interested in quantum-related fields have opportunities to access experimental training, cutting-edge facilities, and advanced instrumentation?
Thank you, Congresswoman, for that question. Representation is so more important, and participation in this is critical towards closing wealth gaps in many cases, particularly for students at underrepresented groups. I think that I want to acknowledge the efforts of DOE Renew program and Expand QASE as initially trying to address this at universities and colleges. It's a complex problem that I'd be happy to provide more in writing. But in short, I will say that Right now, there are early stage activities and initial stage modular curriculum, but we'll need to explore more models out there to find successful ways, particularly because our MSIs, HSIs, community colleges, and primarily undergraduate institutions have professors that are typically tasked with a lot of teaching, and they play an outsized role and a lifeline to their students. And by engaging them in this and providing research funds, we want to make sure we don't risk taking them away from their students and breaking that lifeline. So I'd like to provide more in writing, if that's okay, on this complex question and ideas on how the NQI Act can help move this forward.
Thank you, Mr. Chair. I yield back.
Gentlelady yields back, and now we go to New York with Representative Williams, please. You have 5 minutes.
Thank you, Mr. Chairman. I bring you greetings from Air Force Research Lab in Rome, New York. In our district, we're very proud of that, and Dr. Michael Haydock says hello to many of you that you've worked with in the past. So, yeah, I just want to talk about AFRL and the work that the Air Force is doing, but I'll draw it to something I'd ask for your insight into. AFRL is doing a lot of active R&D programs in quantum information science and principally around clocks, sensing, communications, and computing, much of which has been discussed here today. This groundbreaking research is to support the Air Force and the Space Force in critical issues related to our national defense. And they also have spent a lot of effort around private-public partnerships around the Innovar, the Innovar Center, and working together with academic startups as well as Department of Defense. It's an excellent model, and I'm interested to see particularly how we can pull these things together. As I think about the funding, really for anything, but related to the government, but specifically around quantum science, is there's public funding, like we've discussed for the Air Force or for basic research. There is public-private partnerships. The NQI seems to be well-suited to that and successful. And there's also, of course, a lot of private funding that's taken place. I come out of the tech industry, so I'm always interested in what's happening in Silicon Valley and other areas in these fundamental areas. But my question, and Mr. Secretary, I'll focus it on you just because you and I have spoken about this previously. You know, how can DoD-funded efforts interact with NQIA, NIST, NSF, any of these kinds of funded ventures? How can they interact? Is there things that we can do better?
Yes, Congressman. So I think subject to your committee of jurisdiction and being able to put it into a bill, I think being very explicit in a line item authorizing between DoD and the non-050, so to speak, agencies, the non-DoD agencies, and make it really explicit that they could work together, because sometimes federal agencies get worried, and sometimes staffers say that we're not doing the right thing because it's not in the bill. But I think if you explicitly do that, let me say one thing about AFRL. AFRL is part of a group in New York. Upstate New York is amazing on this topic. AFRL has been the leader, as you said, on many aspects that you just mentioned. But they're part of the group looking to make the bid for the CHIPS Act, DOE, RON, New York Quantum Network. And so there is already cooperation going on between AFRL and the non-military side. And I think making it clear that that's okay, I think would be good.
Great. Anyone else want to add to that?
I'll just say I was up at AFRL Rome last year. It's an amazing place, and I think it's a really great model for everything that we've been talking about today: research security versus fundamental research, public research versus private companies being involved. We welcome the DoD being, more a formal member in the NQI, including the centers. The National Defense Authorization Acts of 20 and 21 and 22, allowed DoD to designate some of those centers as quantum information science centers. But anything more you can do to make that more formal, I think, would be very welcome.
Great. Well, thank you. I just want to point out that Secretary Debarr and I served on submarines contemporarily. We did not overlap in our squadron, but I appreciate your service, and it's not too many times we get shipmates from submarines in the same place without throwing things at each other. So anyway, I'm glad you're here, and I yield back the remainder of my time. Thank you.
Thank you. The gentleman yields back, and now we go to Pennsylvania with Ms. Lee.
Thank you, Mr. Chairman, and thank you all so much for your time and your testimony today. Quantum science conceptually is very difficult for anyone to wrap their heads around, or maybe just me. I'll speak for me. And no less our constituents. However, what I do understand is that quantum technology has the potential to vastly improve the quality of life of folks in my districts and across various fields. In my district, the Pittsburgh Quantum Initiative combines expertise across Duquesne University, the University of Pittsburgh, and Carnegie Mellon in developing new materials, computational science, engineering, and physics to advance quantum computing. Quantum computing, R&D, can and will have a profound impact on industries such as finance and logistics. Investing in quantum sensor R&D will support medical imaging and drug discovery for my district's healthcare workers and help bring cleaner air and water to the Western Pennsylvania region through precision environmental monitoring. While this field is still looking towards the future, our commitments today to supporting further research and development of quantum technology will improve the stability, reliability, and quantum systems to make them more practical and commercially viable for day-to-day applications. So, to anyone, we joked in my office that this hearing will be a great way to talk about Marvel's Ant-Man movies, and if we're closer to making ant suits. We are admittedly a very Gen Z and millennial office. That would, of course, we think, be true American leadership. Realistically, though, why is American quantum leadership an issue that should capture the minds of my constituents in Western Pennsylvania? And what makes something as complex as quantum important to everyday American people?
I'll just start by reminding all of us that we have actually probably no idea of the big killer app that this technology is going to make possible. If you sort of think back or try to put yourself in, 50 years ago and imagine the technology that we have. So the potential is there. We can kind of imagine some of it, but it's really hard to or overestimate how important it's going to be. We can start where we are now, and there are even systems that can do small problems that are useful. How it's going to play out going forward is really hard to predict. But we can sort of envision that it's going to solve these problems that are just outside of where computers today can even touch. And so it's exciting because it's enabling. And I think conveying that to people, the problems that are likely to be solved nearer term, or maybe sort of business problems that are optimizing, financial portfolios or speeding up drug discovery, those are really important. And I think people appreciate them. But there's probably a huge universe of applications that we
haven't even touched yet. Yeah. I understand. Mr. Debarr, what role can we look to see quantum research and technology play in mitigating the multifaceted effects of climate change, like air and water pollution?
Yes, Congresswoman. So one of the interesting pieces of technology I've seen about quantum sensing and about the environment is that I know some people who are doing quantum sensors to more accurately image cloud systems and weather fronts as they're about to come through, and they could very, very accurately figure out how much rain is about to hit. And as a result of that, they could figure out when to plant. Mm-hmm. And there's places in Egypt and in Indonesia and applicable in America of knowing exactly when to plant better. You could increase your yields for your food. You could have a better kind of impact by significant effects. And that's just like one example of looking at the environment, better sensing, and actually taking action as a result of that.
Thank you. Is there an opportunity to leverage the new TIP directorate at NSF to build partnerships between industry and academia for these various purposes?
Absolutely. I mean, I think that's tremendous opportunity in the Science Act. You know, if it's properly funded, it can really try to bring some of these science experiments to actual useful society. I mean, that's really the goal of that. So if we can make that happen, it would really be transformative.
Yeah, I thank you all so much for your time talking to those of us who are not experts in this field, and as we are trying to figure out what our role is in supporting this particular field. Thank you for your patience, and I'm certain that we will continue all these conversations as we are looking into these new fields of discovery and figuring out how we can make life better for all of our constituents. So thank you, and now you'll back.
Gentlelady yields back, and you can relax, witnesses. They tell me that I'm the last one to ask questions, and they aren't really tough, so I think you'll be okay. Is that true? Yeah, okay.
For now.
Anyway, I come from a district in agriculture, West Central Indiana, and so I'm very interested, similar to some of the questions that she asked, but I'm really interested in how well quantum computing deals with agriculture. You know, we have planters today that are very precision oriented, put the seeds exactly where we want. We have harvesters or combines that you go to the end of the field, you hit an auto button and it'll turn around and go back. We have sprayers that can control, you put on less spray and you do it more efficiently. And we even got drones that we can look over the fields with. We've got robots that we can harvest strawberries and so on with. My point is, can you explain to me, Mr. Debarr, I'm going to start with you, briefly how we're using these new technologies in quantum that are working to help agriculture? And you mentioned that a little bit ago, so.
Yes, Congressman. In addition to the water and planting point, which I think can absolutely be implemented with quantum sensing and understanding weather fronts coming through, let me talk to you about fertilizers. So one of the big thing about high performance computing is being able to design, from a chemistry point of view, different products in a much more tailored fashion, much more efficiently, producing it more efficiently, less emissions. So designing of different types of chemicals, and so in this case fertilizers, is a big prospect. High performance computers with current computing capacity has been very valuable, but using computational chemistry to come up with what's next at a much more powerful level, much more detailed, has a great prospect, and we're looking at having that discussion at a workshop here in the fall.
I want to emphasize what you just mentioned, the ability when we had the fertilizer shortage in the last year or so, precision agriculture, and you mentioned being able to having the equipment and the technology, which includes the computer capability, to know where to place. You got soils information, and you know what that seed needs, and so you can strategically place those nutrients. And fertilizer is one of them. So, anyone else have a comment in that regard?
Yeah, I'd be happy to add, underscore some of those things and add a little more detail. I'm just over the border in Illinois, and not too far.
I know where you're at.
Not too far at all. There's a lot of farmland there too, and I think that in the near term, everything you just talked about, I bet relies on some of the advancements in GPS and sensing that are either happened in the latter part of the 20th century or are happening on the ground now. And so I have no doubt that that kind of navigation element will play a critical role. We're a ways off yet from being able to address the fertilizer problem in terms of the scale that we were talking about earlier, to go from 100 qubits to however many it's going to take. And so I think in the near term, continue critical to see applications on the ground in ag tech and other areas that are so critical towards that region of the country.
I'll also add that I believe a lot of the data that you use in agriculture comes from NASA, and that while we'll continue with conventional technologies, quantum sensing and quantum computing can increase both the data rate and the data processing in ways that we can't even imagine how that will end up affecting things.
And I'll just add from the industry perspective that in order for these technologies to go from being research projects to used in the field, there's a lot of industry or private sector players in that chain. And so companies like the big companies that are making the chemicals, that are making the equipment, that are making the software that's going to be run on the combines and drones and everything else, they all need to understand this is coming, and they need to be thinking about how to integrate it into those products. And so the users, what I call the quantum takers, not just the quantum makers, but the takers, need to be learning about this technology too, so that they can put it in the hands of the farmers at the end of the day.
Anyone else? I would just say I want to thank the witnesses for being here. Your input is extremely important to us to try to make decisions. And when you talk about what we were talking in this committee hearing, we're really trying to feed the world, and we're all responsible for trying to make those efforts. And so I just want to thank all of you for being here, and your testimony was extremely important to the members of this committee. The record will remain open for 10 days for additional comments and written questions from the members. And so this hearing is adjourned.